a spiral galaxy drifts through intergalactic space, rotating slowly, quietly over hundreds of millions of years. From a distance, it looks calm, orderly, almost architectural, a glowing disk of stars arranged in a clean, symmetrical plane. But when astronomers turn their telescopes sideways and look at these disks edge on, that apparent order begins to bend, quite literally. Instead of forming a perfectly straight line across the sky, the outer edges of many galactic disks curve upward on one side and downward on the other. Sometimes the bend is gentle and symmetrical, like a soft S traced across the darkness. Sometimes it tilts the same way on both sides, forming a shallow U. In other cases, one side warps dramatically while the other barely moves, producing a lopsided, uneven structure that looks almost damaged. These distortions are not rare curiosities. They are so common that astronomers now consider a flat disk to be the unusual case. A warped galactic disk is not a galaxy that has been twisted violently or torn apart. It is still rotating. It is still gravitationally bound. The inner regions often remain remarkably flat and stable. The warp typically begins far from the centre, where the gravitational grip of the galaxy weakens and the disk becomes more sensitive to its surroundings. Beyond a certain radius, the plane of rotation simply changes direction, gradually, smoothly, as if the galaxy were trying to align itself with something unseen. Observationally, a warp is defined by a systematic change in the orientation of a galaxy's disk as a function of radius. The inner disk rotates in one plane, while the outer disk rotates in another. There is no sharp break, no fracture line. Instead, astronomers see a continuous bending of the disk's mid-plane, traced most clearly by gas, but often echoed, though more faintly, by stars and dust. This distinction matters. Stars move on long, stable orbits and respond slowly to external forces. Gas, by contrast, is dissipative. It cools, collides, flows, and settles. That makes gas an extraordinarily sensitive tracer of subtle gravitational effects. And when it comes to warped disks, gas is where the warp announces itself first and loudest. The clearest evidence comes from observations of neutral hydrogen, the most abundant element in galactic disks. Neutral hydrogen emits radio waves at a wavelength of 21 centimeters, allowing radio telescopes to map gas far beyond the bright stellar disk. These maps often reveal that a galaxy's hydrogen disk extends much farther than its visible stars, sometimes 2 or 3 times farther, and that this extended gas layer is almost never flat. Seen edge-on, these hydrogen disks curve gracefully out of the plane, forming the classic S-shaped warp that has become a visual signature of disk galaxies. The inner regions remain straight, rigid, and aligned, while the outer gas bends upward on one side and downward on the other, maintaining a surprising degree of symmetry. The shape is not random, it is coherent, structured, and stable over long periods of time. In optical light, the same galaxy might look nearly flat. Starlight drops off rapidly with radius, and the outermost stars are faint and difficult to detect. But when astronomers push deeper, stacking long exposures, using wide-field surveys, and tracing stellar populations far into the outskirts, they often find that stars too participate in the warp, though with smaller amplitudes and greater scatter. The warp is not just a gaseous phenomenon, it is a structural feature of the galaxy as a whole. Classic edge-on galaxies such as NGC 4565 and NGC 5907 have become textbook examples. In visible light, their disks appear razor-thin and elegant, but radio observations reveal extended hydrogen layers that bend unmistakably away from the central plane. These warps begin tens of thousands of kilometers, or tens of thousands of miles, from the galactic center in projection, well beyond the region where most of the stars reside. The shapes of these warps vary, but they tend to fall into a few broad observational categories. The most common is the integral sign, or S-shaped warp, where one side of the disk bends upward while the opposite side bends downward. This configuration preserves a kind of mirror symmetry across the galactic centre. U-shaped warps, where both sides bend in the same direction, are less common but still well documented. Asymmetric warps, where one side bends much more strongly than the other, are perhaps the most intriguing because they hint at uneven forces acting on the galaxy. Importantly, these are not static snapshots of chaotic motion. Measurements of gas velocities show that warped disks remain in ordered rotation. The gas in the warped regions follows nearly circular orbits, just tilted relative to the inner disk. This tells astronomers that warps are not transient distortions that appear and disappear quickly. They are long-lived structures, maintained over hundreds of millions or even billions of years. This realization overturned early expectations about how disk galaxies should behave. In the first half of the 20th century, galaxies were often modelled as isolated systems, self-gravitating disks of stars rotating peacefully in space. In such models, a flat disk was the natural outcome. Any bending or twisting was expected to be quickly erased by gravitational forces pulling the disk back into alignment. But the universe did not cooperate with those expectations. As radio astronomy matured in the 1950s and 1960s, astronomers began mapping neutral hydrogen in nearby galaxies. One surprise followed another. Hydrogen disks extended far beyond the optical edge. Rotation curves remained flat instead of declining. And almost everywhere astronomers looked, the outer gas layers were warped. By the 1970s, it was clear that warps were not exceptions caused by rare interactions. They were the norm. Surveys showed that a majority of disk galaxies exhibit some degree of warping when observed deeply enough. Even galaxies that appear isolated with no obvious nearby companions often display pronounced warps in their outer gas disks. This forced a rethinking of what normal means for a galaxy. A perfectly flat disk turns out to be a fragile configuration. It requires that the galaxy's disk, its surrounding dark matter halo, and its ongoing gas accretion all share the same orientation. In the real universe, that alignment is almost never perfect. Galaxies are born in a messy cosmic environment. They grow by accreting gas along filaments, by interacting with smaller companions, and by responding to gravitational fields that change over time. Expecting such systems to remain perfectly planar is, in hindsight, optimistic. Even our own galaxy participates in this quiet distortion. The Milky Way's stellar disk looks flat when we observe nearby stars. But radio surveys of neutral hydrogen reveal that beyond roughly 25,000 kilometers, about 15,500 miles, in projection from the galactic center along the disk, the gas layer begins to bend. On one side of the galaxy, it curves upward. On the other, it dips downward. The warp is asymmetric, and its shape differs slightly between the northern and southern galactic hemispheres. Because we live inside the Milky Way, this warp is difficult to visualize directly, but its effects show up in star counts, gas velocities, and the distribution of dust. The fact that our own galaxy is warped underscores how fundamental this phenomenon is. Warps are not something that happens to other galaxies. They are part of what it means to be a disk galaxy at all. From an observational standpoint, the key lesson is simple but profound. Galactic disks are not rigid objects. They are flexible, responsive structures embedded in a larger gravitational context. The inner regions are dominated by the galaxy's own gravity and tend to remain flat and stable. The outer regions, where gravity is weaker and orbital times are longer, act like sensitive seismographs, recording the influence of forces that are otherwise invisible. This is why warps almost always grow with radius. Near the center, stars orbit quickly and collectively resist bending. Farther out, orbital periods stretch into hundreds of millions of years. Gas is thinner, gravity is weaker, and even gentle torques can slowly reorient the disk. Over cosmic time, those small influences add up. Seen this way, a warp is not a flaw in a galaxy's structure, it is a response. a visible signature of interaction between a disk and its environment. The galaxy is not broken, it is adjusting. And once that idea takes hold, a deeper question naturally follows. If warps are so common, so long-lived and so orderly, what exactly is doing the bending? What forces are strong enough to twist an entire galaxy, yet subtle enough to do it slowly, without tearing the disk apart? Answering that question requires stepping beyond the disk itself into the invisible halos of dark matter that surround galaxies, the slow rain of intergalactic gas, and the gravitational whispers of nearby companions. That is where the real story of warped galactic disks begins. For a long time, astronomers assumed that the Milky Way was a flat system simply because that was the most convenient assumption to make from the inside. When you live embedded within a disk of stars, gas, and dust, perspective becomes deceptive. Nearby stars trace out a thin band across the sky. The Milky Way appears as a luminous, flattened ribbon, suggesting an orderly, planar structure. But that appearance is local. It tells us how the disk behaves near the Sun, not how it behaves as a whole. The first cracks in the idea of a perfectly flat Milky Way appeared not through optical astronomy, but through radio waves. In the mid-20th century, astronomers began to systematically observe the galaxy using the 21-centimetre emission line of neutral hydrogen. This radiation, produced by a subtle quantum transition in hydrogen atoms, passes almost unhindered through interstellar dust. Unlike visible light, it allows astronomers to map gas across the entire galactic disk, including regions completely obscured optically. As radio surveys expanded in the 1950s and 1960s, something unexpected emerged. When astronomers reconstructed the three-dimensional distribution of neutral hydrogen in the Milky Way, they found that the gas layer did not remain confined to a single plane. Beyond the inner regions, the hydrogen disk bent upward in one direction and downward in the opposite direction. The Milky Way, it turned out, was warped. This discovery was not sudden or dramatic. It emerged gradually as data accumulated and models improved. Early hydrogen maps hinted at vertical displacements that could not be explained by local motions alone. By the late 1960s, it became clear that these displacements followed a coherent, large-scale pattern. The outer hydrogen disk systematically departed from the plane defined by the inner galaxy. What made the result compelling was its global symmetry. The warp was not a random corrugation or a series of disconnected bends. It was smooth, continuous, and organized. On one side of the galaxy, the gas layer rose above the midplane. On the opposite side, it dipped below. This geometry closely resembled the S-shaped warps seen in external galaxies viewed edge-on, confirming that the Milky Way was not a special case, merely a familiar one observed from an awkward angle. Mapping this warp required more than simply detecting hydrogen. Astronomers had to translate observed velocities into distances, a non-trivial task when studying a rotating disk from within. By measuring Doppler shifts in the 21-centimetre line and assuming a rotation model for the galaxy, researchers reconstructed the spatial distribution of gas across the disk. Although this method carries uncertainties, especially in the inner regions, the warp in the outer galaxy appeared consistently across different surveys and modelling approaches. The geometry that emerged was striking. The warp begins well outside the Sun's orbit around the galactic centre. Inside this radius, the gas disk remains relatively flat, closely aligned with the stellar disk. Beyond it, the midplane starts to tilt. The displacement grows with distance from the centre, reaching its maximum in the far outer regions. In terms of amplitude, the vertical displacement of the hydrogen layer reaches several thousand light-years above and below the inner disk plane. This is not a subtle ripple. Relative to the thickness of the gas disk itself, the warp represents a large-scale reorientation. The disk is not simply puffed up or flared, it is tilted. The orientation of the warp is also highly structured. It is not aligned randomly with respect to the galaxy's rotation. Instead, it has a well-defined line of nodes. a direction along which the disk crosses the original midplane. On one side of this line, the disk rises, on the other, it falls. This line of nodes is offset from the Sun galactic center line, meaning the warp is asymmetric with respect to our position in the galaxy. That asymmetry matters. The Milky Way's warp is not perfectly symmetric between its northern and southern sides. One side bends more strongly than the other. The onset radius differs slightly. The curvature is smoother in one direction and sharper in the other. These details suggest that the forces shaping the warp are not evenly distributed, and that the galaxy is responding to an external influence with a preferred direction. Crucially, this warp is most pronounced in gas. Neutral hydrogen traces the warp clearly and extensively. Ionized gas follows a similar pattern, though it is more confined to regions influenced by star formation and energetic processes. Molecular gas, which is denser and colder, shows a weaker warp, largely because it is concentrated closer to the galactic plane and inner regions. Stars tell a more complicated story. For decades, it was unclear whether the stellar disk of the Milky Way was warped at all. Early optical surveys lacked the depth and coverage to trace stars far into the outer disk. Moreover, stars have a wide range of orbital inclinations and vertical motions which can blur large-scale patterns. As infrared surveys expanded, allowing astronomers to see through dust and map stellar populations across the galaxy, evidence for a stellar warp accumulated. The stellar disk does warp, but less dramatically than the gas. The amplitude is smaller, and the structure is less coherent. Different stellar populations participate in the warp to different degrees. Younger stars, which formed from the warped gas, tend to follow the gas warp more closely. Older stars, whose orbits were established before the current warp configuration fully developed, show a weaker signal. This difference between gas and stars is a key observational clue. Gas responds quickly to external torques and can dissipate energy through collisions and radiation. When gas is forced into a new orientation, it can settle into a warped configuration relatively efficiently. Stars, by contrast, are collisionless. Once they are on an orbit, changing that orbit requires long-term gravitational influence. As a result, stellar warps lag behind gaseous ones and appear smoother and less sharply defined. Dust adds another layer to the picture. Dust grains are mixed with gas, but they are also strongly influenced by radiation pressure, magnetic fields, and local star formation. Observations of dust lanes and infrared emission show signatures of the warp, but with significant patchiness. Dust traces the warp indirectly, often highlighting regions where the warped gas is dense enough to form stars or block background light. Together, gas, stars, and dust paint a consistent but layered portrait of the Milky Way's warp. The gas reveals the full extent and geometry of the distortion. The stars confirm that the warp is not purely superficial, but a genuine structural feature. The dust shows where the warped disk intersects regions of active galactic life. One of the most important insights from these observations is that the Milky Way's warp is not static. Different surveys taken decades apart show subtle differences in amplitude and shape. This suggests that the warp may evolve over time, precessing or responding to changing external conditions. However, any such evolution is slow, unfolding over hundreds of millions of years. On human timescales, the warp is effectively permanent. Understanding the Milky Way's warp also requires recognizing what it is not. It is not a simple tilt of the entire galaxy. The inner disk remains well-defined and relatively flat. The Sun's local neighborhood lies close to this inner plane, which is why the Milky Way appears flat to us. The warp begins farther out, beyond the region where most visible stars are concentrated. This layered structure explains why the warp went unnoticed for so long. Optical astronomy naturally emphasizes the inner disk, where starlight is abundant. Radio astronomy, by contrast, is sensitive to diffuse gas far from the center. Only when astronomers combined these perspectives did the full structure emerge. From a broader perspective, the Milky Way's warp places our galaxy firmly within the population of warped disk galaxies observed across the universe. There is nothing exotic or unusual about it. In fact, its properties, the dominance of gas, the asymmetric shape, the outer disk onset, closely resemble those seen in external spirals. That realization has profound implications. It tells us that whatever mechanisms warp other galaxies are also at work here. The Milky Way is not isolated, it is embedded in a larger gravitational environment. It accretes gas, it interacts however subtly with its surroundings. The warp, then, is not merely a geometric curiosity, it is a record, a visible imprint of forces acting on the galaxy over cosmic time. By studying its amplitude, orientation, and asymmetry, astronomers gain insight into the invisible structures around the Milky Way. The distribution of dark matter, the flow of intergalactic gas, and the gravitational influence of nearby companions. Seen from the inside, the Milky Way feels calm and stable. But when traced in hydrogen across its full extent, it reveals a quiet twist, a slow bending that tells a deeper story about how galaxies live within the universe. When astronomers first began to study galaxies beyond the Milky Way in any systematic way, they did so with a set of expectations inherited from classical mechanics and early stellar dynamics. A rotating disk of matter bound by gravity should settle into a flat, stable configuration. Any deviation from that plane should be temporary, quickly erased by the collective pull of the disk's own mass. In that framework, a flat galaxy was not just aesthetically pleasing, it was dynamically inevitable. This expectation was reinforced by the limitations of early observations. Optical telescopes in the first half of the 20th century were most sensitive to bright stellar light. They traced the inner regions of galaxies, where stars are densely packed and gravity is strong. Those regions do appear remarkably flat. Dust lanes in edge-on spirals form narrow, straight bands. Stellar disks, where visible, often look razor-thin. The faint outskirts, where deviations from planarity are most pronounced, were largely invisible, so when the first hints of warped galactic disks appeared, they did not arrive as a dramatic revelation. They emerged slowly, unevenly, almost reluctantly, as new techniques pushed observations beyond the bright stellar core. The mid-20th century marked a turning point. Radio astronomy matured rapidly after the Second World War, driven in part by advances in radar technology. Astronomers discovered that neutral hydrogen, abundant in galaxies, emits radiation at a wavelength of 21 centimeters. Unlike visible light, this emission could be detected far beyond the optical edge of a galaxy. It could also be observed regardless of dust obscuration. For the first time, galaxies could be mapped not just where they were bright, but where they were massive. Early radio surveys of nearby spiral galaxies began to reveal extended hydrogen disks that dwarfed their stellar counterparts. These disks reached far into space, tracing the true gravitational extent of galaxies. And within these extended structures, astronomers noticed something unsettling. The gas did not lie neatly in a single plane. One of the earliest extragalactic cases came from studies of nearby edge-on spirals in the 1950s and 1960s. When radio contours were overlaid on optical images, the gas layers appeared to bend away from the mid-plane defined by the stars. At first, these bends were treated cautiously. Could they be artifacts of projection, errors in velocity modelling, confusion with foreground or background gas? As more galaxies were observed, the pattern became impossible to dismiss. The bending was coherent, symmetric, and repeatable. Different telescopes, different observing teams, different galaxies. The result was the same. Beyond a certain radius, the disks curved. What made these discoveries particularly striking was their regularity. The warps were not chaotic distortions. They were smooth, continuous, and often mirrored on opposite sides of the galaxy. In many cases, the inner disk appeared rigid and flat, while the outer disk peeled away like the edge of a vinyl record left too close to heat. This structure did not fit comfortably within existing models. Classical disk equilibrium theory treated galaxies as largely isolated systems. Once a disk formed, it was expected to remain stable unless acted upon by a strong perturbation, such as a major collision. Minor disturbances should damp out quickly. Differential rotation would smear them away. Self-gravity would restore planarity. Yet here were disks that appeared to be persistently bent, with no obvious signs of recent violent interactions. Some of the most striking warped galaxies showed no nearby companions, no tidal tails, no obvious scars of collision. They looked, in every other respect, like ordinary, undisturbed spirals. This raised an immediate question. If these galaxies had not been recently disrupted, why hadn't their disks flattened out? The challenge went deeper than morphology. Kinematic data showed that the gas in warped regions was not tumbling or falling out of the galaxy. It was rotating in an orderly fashion, following nearly circular orbits, just tilted relative to the inner disk. This implied that the warp was dynamically supported. It was not a transient oscillation, but a stable configuration. That realization was deeply uncomfortable for equilibrium models. In a purely self-gravitating disk, a warp should precess at different rates at different radii. Over time, this differential precession should twist the warp into a tangled mess and erase it. The fact that real warps remained coherent suggested that something was missing from the theoretical picture. Initially, some astronomers attempted to preserve the flat disk paradigm by treating warps as rare or short-lived phenomena. Perhaps they were the result of recent interactions that had simply not yet damped out. Perhaps the observed galaxies were caught at a special moment, but as surveys expanded, that explanation became untenable. By the 1970s, it was clear that a majority of spiral galaxies exhibited warps when observed deeply enough. If warps were short-lived, galaxies would have to be constantly perturbed to maintain such a high fraction. That implied a level of interaction that contradicted observations. Others proposed internal mechanisms. Could bending instabilities within the disk generate persistent warps? Could collective modes allow the disk to oscillate without damping? Some theoretical work explored these possibilities, but they struggled to reproduce the observed large-scale coherence and longevity of warps without fine-tuning. A deeper conceptual shift was required. The first cracks in the isolated disk assumption appeared alongside another, equally disruptive discovery. The realization that galaxies are embedded in massive, extended halos of unseen matter. Rotation curves measured in the 1970s showed that stars and gas orbit far faster than visible matter alone could support. Galaxies, it seemed, were dominated by dark matter. This realization reframed the warp problem. If the visible disk was only a small component of a much larger gravitational system, then its equilibrium could not be understood in isolation. The disk's plane might not align with the principal axis of the surrounding halo. Even a small misalignment could produce torques that slowly twist the outer disk. At the time of the earliest warp discoveries, however, this framework had not yet fully crystallized. Astronomers were still grappling with the basic mass distribution of galaxies. Warps, in this sense, were an early warning sign, observational evidence that the visible disk was not the whole story. Another assumption challenged by early warp observations was the idea that galaxies were dynamically mature objects. Classical models implicitly assumed that once a disk formed, it settled into a steady state and remained there for most of cosmic time. Warps suggested ongoing evolution. They hinted that galaxies might still be responding to their environment long after their initial formation. This was a subtle but profound shift. A warped disk implies that a galaxy is not dynamically closed. It is exchanging angular momentum with something external. Gas, satellites, or a surrounding mass distribution that does not share the disk's orientation. The disk is not merely rotating, it is negotiating. By the late 20th century, warps had gone from curiosities to constraints. Any successful theory of disk galaxies now had to explain not only why disks form and rotate, but why they bend, and why that bending persists. In hindsight, it is striking how closely the observational timeline of warp discoveries parallels the broader transformation of galactic astronomy. Warps were identified just as radio astronomy expanded observational reach. They became unavoidable just as dark matter entered the theoretical landscape. They resisted explanation just as the idea of galaxies as isolated systems began to dissolve. What early astronomers thought they were seeing, minor imperfections on otherwise flat disks, turned out to be fundamental clues. The warps were telling them that galaxies are embedded in larger structures, influenced by forces that act gently but relentlessly over billions of years. Flat disks were not wrong exactly, they were incomplete. The classical picture assumed symmetry, isolation, and equilibrium. Warped disks revealed asymmetry, openness, and ongoing interaction. They forced astronomers to think beyond the visible stars, beyond the optical edge, beyond the comforting simplicity of planar systems. And once that door was opened, it could not be closed again. The challenge laid down by those early observations still echoes today. Any explanation for warped disks must account for their ubiquity, their coherence, and their longevity. It must explain why the inner disk remains flat while the outer disk bends. It must work not just for peculiar galaxies, but for ordinary ones, including our own. In that sense, warped disks were among the earliest observational signs that galaxies live complicated lives. Long before simulations grew sophisticated, long before dark matter halos were mapped in detail, the bends in galactic disks were quietly pointing to a deeper, richer dynamical reality. They were telling astronomers that galaxies are not rigid plates spinning in empty space. They are flexible systems, embedded in invisible structures, shaped continuously by forces that are subtle, persistent, and profoundly non-local. And it is only by taking those forces seriously that the warps begin to make sense. A disk galaxy does not exist on its own. Long before astronomers had names for its spiral arms or mapped its gas, it was already embedded in something much larger, heavier, and invisible. The stars, dust, and gas that define the visible disk make up only a small fraction of the galaxy's total mass. Surrounding them is a vast halo of dark matter, extending far beyond the luminous edge, dominating the gravitational field in which the disk lives. Once this picture became clear, warped galactic disks stopped looking like anomalies and started looking like consequences. Dark matter halos are not thin, delicate structures. They are massive, extended, and dynamically slow. A typical halo stretches hundreds of thousands of light years from the galactic center, enveloping the disk in a gravitational cocoon. The disk rotates rapidly, completing an orbit in a few 100 million years. The halo, by contrast, evolves over much longer timescales. Its shape and orientation change slowly, responding to the galaxy's growth, mergers, and cosmic environment. Crucially, there is no fundamental reason for the disk and the halo to be perfectly aligned. Galactic disks form from cooling gas that collapses within the gravitational potential of a dark matter halo. But the angular momentum of that gas is acquired through complex processes, tidal torques from the surrounding large-scale structure, anisotropic accretion along cosmic filaments, and the cumulative effect of minor mergers. The resulting disk settles into a plane defined by the angular momentum of the gas at the time of its formation. The dark matter halo, however, retains memory of earlier stages, accretion events, and interactions that may not share that same orientation. The outcome is subtle but powerful. A disk embedded in a halo whose symmetry axis does not match the disk's rotation axis. This misalignment is the starting point for warps driven by dark matter halos. If the halo were perfectly spherical, misalignment would not matter. A sphere exerts the same gravitational pull in all directions, but real dark matter halos are not spherical. Numerical simulations show that they are typically triaxial, elongated along three unequal axes, with shapes that range from mildly oblate to strongly prolate. Even when they appear roughly round, small deviations from symmetry are enough to matter over cosmic time. A triaxial or tilted halo exerts torques on the disk. These torques are not violent. They do not rip stars from their orbits or shatter the disk. Instead, they act slowly, steadily, like a gentle but persistent twist applied over billions of years. The inner disk, where gravity from the stars themselves is strong, resists this twisting. The outer disk, where the halo dominates the gravitational field, responds. This naturally produces a warp. The physics is conceptually simple. Each ring of material in the disk feels a gravitational pull from the halo. If the halo's mass distribution is tilted relative to the disk, that pull is not symmetric about the disk plane. The result is a torque that tries to reorient the ring's angular momentum. Inner rings are tightly coupled to one another by the disk's self-gravity, so they behave almost like a rigid plate. Outer rings are more weakly bound and more weakly coupled. They begin to tilt, gradually shifting their orbital planes. The warp is the smooth transition between these two regimes. One of the most compelling features of halo-driven warps is that they naturally explain why warps begin at large radii. Near the centre of the galaxy, the stellar disk dominates the gravitational potential. Stars and gas are locked into a common plane by their mutual gravity. Farther out, the disk's surface density drops. The halo's influence grows. That is precisely where warps are observed to appear. Halo-driven models also explain why warps are long-lived. This was a major stumbling block for earlier theories. In a purely self-gravitating disk, a warp should wind up due to differential precession. Different radii precess at different rates, quickly destroying coherent structure. But when the dominant gravitational field comes from an external halo, the situation changes. The halo imposes a preferred orientation. As long as the halo's shape and orientation remain relatively stable, the torques it applies remain coherent. The disk is not freely precessing, it is being guided. The warp becomes a quasi-steady configuration rather than a transient wave. In effect, the outer disk is trying to align with the halo, while the inner disk resists. The compromise is a warp. This picture becomes even more compelling when the halo itself is allowed to evolve. Dark matter halos grow through mergers and continuous accretion. Each event can slightly alter the halo's shape or orientation. When that happens, the direction of the torque changes. The disk responds slowly, adjusting over time. The result can be a warped disk whose shape evolves gently rather than remaining fixed. Importantly, this evolution is slow enough that the disk is never violently disrupted. Stars remain on near-circular orbits. Gas continues to rotate smoothly. The warp persists not because nothing is happening, but because something is always happening, just gradually. Simulations play a crucial role in testing this idea. When disk galaxies are embedded in triaxial dark matter halos with misaligned axes, warps emerge naturally. The shape, amplitude, and radial dependence of the simulated warps closely resemble those observed in real galaxies. The inner disk stays flat. The outer disk tilts. The transition is smooth, and the structure persists for billions of years. One of the key results from these simulations is that the exact shape of the warp depends sensitively on the halo's geometry. A mildly flattened halo produces gentle, symmetric warps. Strongly triaxial halos can produce asymmetric or even lopsided warps. Time-dependent halo reorientation can generate more complex structures, including twisted or multi-component warps. This sensitivity turns warps into diagnostic tools. By studying the geometry of a warp, astronomers can infer properties of the surrounding dark matter halo that would otherwise be impossible to measure. The warp becomes a visible response to an invisible structure. There is another subtle but important aspect to halo-driven warps. Alignment is never fully achieved. Even over billions of years, the disk does not simply settle into the halo's plane. The inner disk's self-gravity acts as a stabilizing force, anchoring it to its original orientation. This prevents the warp from propagating inward indefinitely. Instead, the disk maintains a flat inner region and a warped outer region, separated by a transition zone. This explains why warps do not grow without bound. They saturate. The amplitude increases with radius but eventually reaches a steady configuration. The disk is neither perfectly flat nor completely twisted. It exists in a state of controlled distortion. From this perspective, a flat disk is not the default outcome of galactic dynamics. It is a special case that requires alignment between disk and halo. Given the complexity of galaxy formation, such alignment is unlikely to be perfect for long. Warps are the expected result of realistic initial conditions. This framework also sheds light on the asymmetries observed in many warps. If the halo is not symmetric, if it is elongated or clumpy, then the torques it exerts will vary with azimuth. One side of the disk may experience a stronger torque than the other. The result is an asymmetric warp, exactly as observed in many galaxies, including the Milky Way. Crucially, halo-driven warps do not require recent interactions. They do not depend on close encounters or dramatic mergers. A galaxy can appear isolated and still be warped, simply because its disk and halo are not aligned. This resolves a long-standing observational puzzle. Why do apparently undisturbed galaxies so often show warps? The answer is that the disturbance is not external in the usual sense. It is built into the galaxy's gravitational architecture. This does not mean that other mechanisms are irrelevant. Gas accretion, satellite interactions, and magnetic fields can all contribute to warp formation and evolution. But the dark matter halo provides the underlying framework that allows warps to exist and persist. It sets the stage on which other processes act. Perhaps the most profound implication of halo-driven warps is conceptual. It forces a shift in how galaxies are understood. The visible disk is not the primary determinant of galactic structure. It is a responsive component, embedded within a larger dominant system. Its shape reflects not only its own dynamics, but the geometry and history of the dark matter halo around it. In this sense, warped disks are not merely bent disks. They are maps. They trace the orientation, symmetry, and evolution of invisible mass. They reveal that galaxies are not rigid, self-contained objects, but flexible systems negotiating with their gravitational environment. The quiet twist of a warped disk is the visible imprint of that negotiation, a record of misalignment, persistence, and slow cosmic adjustment. Once this perspective is adopted, the ubiquity of warps stops being surprising. It becomes inevitable. A galaxy is never finished. Even long after its main disk has formed and settled into rotation, it continues to interact with its surroundings in a slow, almost imperceptible way. Gas drifts in from intergalactic space, guided by gravity, shaped by large-scale structure, and carrying with it a memory of where it came from. This quiet, continuous inflow is one of the most important and most underestimated drivers of warped galactic disks. Cosmic gas accretion is not a rare event confined to the early universe. It is an ongoing process. Galaxies sit at the intersections of filaments in the cosmic web, embedded in diffuse reservoirs of hydrogen that stretch across millions of light years. Over billions of years, gas from these reservoirs flows inward, feeding star formation, replenishing disks, and subtly reshaping galactic structure. Unlike the gas that formed the original disk, newly accreted material does not necessarily arrive neatly aligned with the existing plane of rotation. Its angular momentum is set by the geometry of the cosmic web, by the filament along which it travels, and by the gravitational torques it experiences along the way. There is no reason for that angular momentum vector to match the one defined by the disk that already exists. This mismatch is crucial. Angular momentum determines the plane in which gas settles once it cools and circularizes. If infalling gas carries angular momentum tilted relative to the disk, it cannot immediately join the disk's rotation without consequence. Instead, it settles into orbits that are inclined, forming a tilted outer layer. Over time, as more misaligned gas accumulates, a warp emerges. This process is remarkably gentle. There is no violent collision, no shock strong enough to disrupt the disk. The gas arrives gradually at low densities over timescales measured in hundreds of millions to billions of years. But because the process is persistent, its effects accumulate. The outer disk slowly bends to accommodate the new material. Observationally, this picture fits strikingly well with what astronomers see. Warps are strongest in the outer regions of galaxies, exactly where newly accreted gas is expected to settle. They are more pronounced in gas than in stars, consistent with gas being the primary recipient of fresh angular momentum. And they are common even in galaxies that appear isolated, because cosmic gas accretion does not require nearby companions. The intergalactic medium-feeding galaxies is not uniform. Gas flows along filaments that are themselves oriented in specific directions relative to the galaxy. These directions can change over time as large-scale structure evolves. As a result, the orientation of incoming gas can drift. The disk is then forced to respond not to a single misalignment, but to a slowly varying one. This naturally produces warped and sometimes twisted outer disks. Simulations of galaxy formation strongly support this scenario. When gas accretion is allowed to proceed self-consistently along cosmic filaments, disks rarely remain perfectly flat. Instead, their outer regions continually adjust to the changing angular momentum of incoming material. The inner disk remains relatively stable, anchored by its own mass and by the stars that dominate its gravitational potential. The outer disk becomes a flexible interface between the galaxy and its environment. One of the most important consequences of this process is that gaseous warps are typically stronger and more coherent than stellar warps. Gas behaves very differently from stars. It is collisional and dissipative. When gas streams intersect or encounter the existing disk, they can shock, cool, and lose energy. This allows gas to settle efficiently into a new configuration defined by its angular momentum. If that angular momentum is misaligned, the gas does not fight it. It follows it. Stars, by contrast, are collisionless. They cannot radiate away energy or adjust their orbits easily. Once a star is on a particular orbit, changing that orbit requires sustained gravitational torques over long timescales. As a result, stars respond sluggishly to changes in disk orientation. This difference explains a key observational fact. Gas warps are sharp, extended, and clearly defined, while stellar warps are smoother, weaker, and often harder to detect. In many galaxies, the neutral hydrogen disk extends far beyond the stellar disk. This outer gas is precisely the region most exposed to incoming material. When misaligned gas settles there, it creates a pronounced warp with little resistance. The stars, concentrated closer to the center, feel the effects only indirectly. Over time, some stellar populations may be pulled into slightly tilted orbits, especially younger stars that form from the warped gas. Older stars, however, retain memory of the disk's earlier orientation. This leads to an age-dependent warp signature. Young stars trace the gas warp more closely. Intermediate-age stars show a muted version. Old stellar populations may appear almost unwarped at all. Observational studies of stellar populations across galactic disks support this layered picture. Dust follows the gas, but imperfectly. Dust grains are embedded in gas clouds, but they are also influenced by radiation pressure, magnetic fields, and feedback from star formation. As a result, dust warps tend to be patchy. They highlight the warp where gas density is high enough to form stars or obscure background light, but they do not trace the full geometry as cleanly as neutral hydrogen does. The strength of gaseous warps is also enhanced by the fact that gas disks are thinner and dynamically colder than stellar disks. Gas has lower velocity dispersion. It moves on more nearly circular orbits. This makes it more sensitive to small torques. A given misalignment in angular momentum produces a larger geometric response in gas than in stars. Over cosmic time, this continuous accretion-driven warping can maintain a disk in a perpetually warped state. Even if one episode of accretion subsides, another may follow from a slightly different direction. The disk is never allowed to fully relax into a single plane. Instead, it remains gently twisted, especially at large radii. This perspective resolves a long-standing puzzle. Why warps are so common, yet often show no obvious trigger. If warps required close encounters or dramatic mergers, they should be rare. But if they arise from the normal process of galaxy growth, the steady inflow of intergalactic gas, then their ubiquity is not surprising at all. It also explains why warps can coexist with otherwise undisturbed disks. Gas accretion is subtle. It does not leave tidal tails or shells. It does not disrupt spiral arms. It simply adds mass and angular momentum in a way that the disk must accommodate. There is an important interplay here between gas accretion and dark matter halos. The orientation of incoming gas is not random. It is influenced by the gravitational field of the halo and by the structure of the cosmic web feeding it. In many cases, the angular momentum of accreted gas is misaligned not only with the disk, but also with the halo's principal axes. This compounds the effect, reinforcing halo-driven warps and making them more persistent. In this combined picture, warps are not caused by a single mechanism. They are the visible result of multiple gentle influences acting together. A misaligned halo providing a background torque, and ongoing gas accretion continually delivering angular momentum that does not quite match the disk. This helps explain the diversity of observed warp shapes. Symmetric S-shaped warps may arise when accretion is relatively steady and aligned in a consistent way. Asymmetric warps may result from lopsided or time-variable inflow. U-shaped warps may reflect large-scale bending modes excited by coherent accretion along a dominant filament. At higher redshifts, where gas accretion rates were higher and more chaotic, warps are expected to be stronger and more irregular. Observations of distant disk galaxies support this expectation. Their disks often appear thicker, more turbulent and more distorted. As accretion rates decline over cosmic time, disks settle, but they rarely become perfectly flat. From this viewpoint, a flat disk is not the natural endpoint of galaxy evolution. It is a temporary state that can exist only when accretion slows and alignment happens to be favourable. Given enough time, misalignment returns. Perhaps the most striking implication of accretion-driven warps is philosophical rather than technical. It reinforces the idea that galaxies are open systems. They are not sealed islands of stars rotating in isolation. They are interfaces between the visible universe and a vast, diffuse reservoir of matter that is still flowing, still interacting, still shaping structure. The warp is the signature of that interaction. Every bend in a gaseous disk is a record of where gas came from, how it fell in, and how its angular momentum differed from what was already there. In this sense, warped disks are historical documents. They encode the growth history of galaxies in their geometry. Gas tells that story most clearly because it is still listening to the universe. Stars, once formed, largely stop listening. They remember the past, but they respond slowly to the present. Gas responds immediately. That is why gaseous warps are stronger, not because gas is weaker, but because it is more honest. It moves where gravity and angular momentum tell it to move, without the inertia of long-lived orbits. It bends when the galaxy bends. It traces the negotiation between a disk and the cosmic environment that feeds it. And as long as galaxies continue to accrete gas, quietly, persistently, inevitably, warped disks will remain a defining feature of spiral galaxies across the universe. A galaxy does not travel through the universe alone. Even when it appears isolated, drifting quietly through intergalactic space, it is almost always accompanied by smaller companions. Dwarf galaxies orbit larger hosts. Faint satellites loop around massive disks on elongated paths. Remnants of past mergers linger as streams and shells. Together, these companions form a dynamic, constantly changing environment that exerts subtle but persistent gravitational influence. These influences rarely announce themselves dramatically. They do not usually tear disks apart or trigger spectacular bursts of star formation. Instead, they act through tidal torques, weak gravitational forces that accumulate slowly, shaping galaxies over immense spans of time. When it comes to warped galactic disks, these gentle interactions often matter far more than the rare, violent encounters that dominate popular imagination. Satellite galaxies are typically thousands to millions of times less massive than their hosts. On their own, they seem insignificant. A single dwarf companion passing nearby might raise a slight distortion, a faint ripple in the outer disk, easily dismissed as transient. But satellites do not act once. They orbit, they return, and over billions of years their repeated passages leave an imprint. Each orbit applies a small torque to the disk. The strength of that torque depends on the satellite's mass, its distance at closest approach, and the orientation of its orbit relative to the disk. Individually, these torques are weak. Collectively, they are persistent. The outer regions of a galactic disk are especially vulnerable. There, the gravitational binding is weaker. Orbital periods are long. Material responds slowly, allowing perturbations to accumulate rather than cancel out. This makes the outskirts of disks natural recorders of tidal influence. Over time, these influences bend the disk, lifting one side and depressing the other, creating the familiar warped geometry. One of the most important realizations in modern galactic dynamics is that repeated weak interactions do not average away. They add up. Early models often assumed that only major mergers or close encounters could significantly alter disk structure. Minor interactions were treated as noise, disturbances that might briefly perturb a disk but would quickly damp out. That assumption turns out to be wrong. In a rotating disk, a steady or recurring torque produces a systematic response. Each time a satellite passes through pericenter, it nudges the disk in roughly the same way. The inner disk, tightly bound by self-gravity, resists. The outer disk yields. Over many orbits, the disk slowly reorients itself at large radii, while remaining flat closer in. The result is a warp. This process is inherently cumulative. A satellite does not need to be massive if it is persistent. Even low-mass dwarfs can induce significant warps if they orbit for long enough and with the right geometry. In fact, satellites on inclined or polar orbits are particularly effective because their gravitational pull is directed out of the disk plane. The geometry matters as much as the mass. A satellite orbiting within the plane of the disk primarily excites spiral structure and density waves. One orbiting above or below the plane preferentially excites bending modes. Over time, these bending modes settle into large-scale warps rather than transient ripples. Minor mergers, events in which a small galaxy is gradually absorbed by a larger one, amplify this effect. As a dwarf galaxy spirals inward due to dynamical friction, it exerts torques on the disk at each stage of its descent. The merger itself may not be visually dramatic, there may be no obvious tidal tails or starbursts, but the disk feels the interaction continuously. Even after the satellite is fully disrupted, its influence does not disappear. The debris spreads out along the orbit, forming stellar streams and diffuse dark matter structures. These remnants continue to exert gravitational influence, maintaining or even reshaping the warp long after the original companion is gone. This is why warps are often observed in galaxies with no obvious nearby satellites. The culprit may already have dissolved. Another key point is that satellite-induced warps do not require a single dominant companion. In many systems, multiple dwarfs orbit the host galaxy on different planes and with different periods. Their combined gravitational field is time-dependent and asymmetric. The disk is subjected not to a steady torque, but to a fluctuating one. This variability can produce asymmetric warps, where one side of the disk bends more strongly than the other. It can also cause the line of nodes, the direction along which the disk crosses its inner plane, to drift over time. Observationally, such asymmetries are common, reinforcing the idea that multiple weak perturbers are often at work. Crucially, this framework explains why warps persist without requiring constant fine-tuning. The disk is never given enough time to fully relax. Before one perturbation can damp out, another arrives. The disk exists in a state of ongoing adjustment, always responding, never settling completely. This contrasts sharply with the effects of major mergers. When two galaxies of comparable mass collide, the outcome is dramatic. Disks are shredded, orbits are randomized. The remnant may become an elliptical galaxy, losing its disk entirely. Warps are irrelevant in this regime because the disk itself does not survive. Minor mergers and satellite interactions operate in the opposite limit. They preserve the disk while reshaping it. They are quiet sculptors rather than catastrophic destroyers. This distinction matters because major mergers are rare, especially in the later universe. Most disk galaxies have not experienced a major merger for billions of years. If warps depended on such events, they would be uncommon. Instead, warps are ubiquitous. Minor interactions, by contrast, are inevitable. Almost every galaxy has satellites. Almost every galaxy experiences a steady drizzle of small companions over cosmic time. From a statistical standpoint, repeated weak interactions are the dominant mode of galactic evolution. Simulations strongly support this view. When realistic populations of satellite galaxies are included in models of disk evolution, warps arise naturally. The amplitude and shape of the warp depend on the distribution of satellite orbits and masses. Systems with more inclined satellites show stronger warps. Systems with more symmetric satellite distributions show milder ones. Importantly, these simulated warps resemble observed ones not just qualitatively, but quantitatively. Their radial extent, asymmetry, and persistence match what astronomers see in real galaxies. Another subtlety emerges from these models. Satellites interact not only with the disk, but with the dark matter halo as well. As a satellite orbits, it perturbs the halo, creating wakes and density enhancements. These halo distortions then exert additional torques on the disk, amplifying the effect. In this way, satellite-induced warps are often mediated by the halo. The disk does not feel the satellite directly as much as it feels the halo's response to the satellite. This coupling allows even low-mass companions to have outsized influence because they leverage the halo's mass. This mechanism also explains why satellite-induced warps can be long-lived. Once the halo is perturbed, it can retain memory of the interaction for billions of years. The disk then responds to a persistent, large-scale distortion in the gravitational field, not just to a fleeting encounter. From an observational perspective, this helps explain why some warps appear aligned with known satellite systems, while others do not. In some cases, the connection is direct and obvious. In others, the satellite responsible may have already merged or may be influencing the disk indirectly through the halo. The cumulative nature of tidal torques also explains why warp amplitude often correlates weakly with obvious interaction signatures. A galaxy may show a pronounced warp without tidal tails, shells, or starburst activity. Those dramatic features fade relatively quickly. Warps driven by long-term torques endure. This endurance can be misleading. It can make warps look static, almost primordial. In reality, they are dynamic structures constantly maintained by ongoing interactions. Their apparent stability is the result of balance, not inactivity. Over billions of years, the disk learns the pattern of its environment. It bends where the torques are strongest. It resists where self-gravity dominates. It adjusts slowly, maintaining coherence while responding to change. This perspective shifts how satellite galaxies are viewed. They are no longer just minor players or future merger debris. They are active participants in shaping disk structure, even when their influence is subtle. It also reframes the meaning of isolation. A galaxy can be isolated in appearance, but not in effect. Its environment may be faint, diffuse, or already assimilated, yet its gravitational fingerprints remain etched into the disk. Repeated weak interactions matter more than rare dramatic events because they operate continuously, universally, and cumulatively. They do not rely on chance collisions. They are built into the hierarchical nature of cosmic structure formation. In a universe where galaxies grow by accreting smaller systems, warps are not accidents. They are records. Each bend in the disk carries the memory of a satellite's passage, a minor merger's torque, a gravitational whisper repeated countless times. Together, those whispers become a visible twist, a long-lived distortion that tells the story of a galaxy's slow, patient interaction with its surroundings. The warp is not the scar of a single encounter, it is the sum of many. By the time warped disks were firmly established as a common feature of spiral galaxies, astronomers had exhausted the simplest gravitational explanations. Disks were bending without obvious collisions. Some galaxies were isolated, others showed warps that were coherent, long-lived, and remarkably regular. This opened the door to more unconventional ideas, and among them one stood out for its elegance and ambition. Large-scale galactic magnetic fields. Magnetic fields are invisible, pervasive, and capable of exerting forces without direct contact. They thread through galaxies, couple strongly to ionized gas, and extend far beyond the bright stellar disk. At first glance, they seemed almost perfectly suited to the problem. If gravity alone could not easily maintain a warp, perhaps magnetism could. Interest in magnetic warping models rose sharply in the 1960s and 1970s, alongside the first serious measurements of galactic magnetic fields. Radiopolarization observations revealed that spiral galaxies host coherent magnetic structures spanning tens of thousands of light years. These fields are not chaotic tangles. They are ordered on galactic scales, often following spiral patterns and extending into the outer disk. The key insight was simple. Gas in galactic disks is electrically conducting. When conducting gas moves through a magnetic field, it experiences magnetic tension and pressure forces. If the magnetic field is oriented differently from the disk plane, it can exert vertical forces on the gas. In principle, this could lift parts of the disk above or below the midplane, producing a warp. Early magnetic warp models imagined large-scale magnetic fields threading the disk and connecting it to the intergalactic medium. If those external fields were inclined, they could pull on the outer gas disk like invisible wires, bending it upward on one side and downward on the other. The inner disk, more massive and more tightly bound, would resist. The outer disk would yield. The result, at least on paper, looked very much like an observed warp. This idea had immediate appeal for several reasons. First, it naturally explained why warps are strongest in gas. Magnetic forces act directly on ionized gas, but have no direct effect on stars. Second, magnetic fields extend well beyond the optical disk, matching the radial range where warps are observed. Third, magnetic fields evolve slowly, offering a potential explanation for warp longevity. For a time, magnetic warps were taken seriously as a primary explanation. Some models proposed that the galactic disk was threaded by vertical magnetic fields anchored in the surrounding intergalactic medium. Others suggested that azimuthal fields within the disk could generate bending stresses when twisted by differential rotation. Still others explored hybrid scenarios, where magnetic fields amplified or sustained warps initially generated by gravitational effects. But as observational data improved and theoretical analysis deepened, cracks began to appear. The first major issue was strength. Galactic magnetic fields, while extensive, are weak in absolute terms. Typical field strengths in spiral galaxies are a few microgauss. These fields are dynamically important for cosmic rays and interstellar turbulence, but when compared to gravity on galactic scales, their influence is limited. To produce the observed amplitudes of warps, vertical displacements of thousands of light years, magnetic fields would need to exert forces comparable to gravitational torques from dark matter halos or satellite galaxies. Detailed calculations showed that under realistic conditions, magnetic forces fall short by orders of magnitude. They can perturb gas locally, but they struggle to bend an entire outer disk coherently. Even more problematic was geometry. Magnetic fields in galaxies are not rigid structures. They are frozen into the gas and are carried along by galactic rotation. Differential rotation: the fact that inner parts of a galaxy rotate faster than outer parts wins magnetic field lines over time. Any initially coherent vertical or inclined magnetic structure is quickly twisted into a tightly wound spiral. This winding problem is fatal for long-lived warps. If a magnetic field were responsible for holding a warp in place, its orientation would need to remain coherent over billions of years. But differential rotation destroys such coherence on much shorter timescales. The field lines wrap up, magnetic stresses redistribute, and the vertical forces average out. Instead of maintaining a smooth warp, the disk would develop tangled distortions or rapidly damp back toward the midplane. Some models attempted to evade this by invoking continuous regeneration of the magnetic field through dynamo processes. Galactic dynamos can indeed sustain large-scale magnetic fields, but dynamos generate fields aligned with the disk's rotation and symmetry. They do not naturally maintain a persistent tilt relative to the disk plane. In fact, dynamo theory predicts fields that reinforce disk symmetry, not break it. Another serious challenge came from the observed symmetry of warps. Many galactic warps are highly symmetric S-shapes, with a well-defined line of nodes. Magnetic forces, especially those tied to turbulent interstellar gas, tend to produce more irregular structures. They are sensitive to local conditions, star formation, supernova feedback, gas density variations. Yet warps are smooth on scales far larger than any of these processes. If magnetism were the dominant driver, one would expect warps to correlate strongly with regions of enhanced star formation or ionization. Observationally, they do not. Warps persist in quiescent outer disks, where star formation is minimal and magnetic coupling is weaker. The problem becomes even sharper when stars are considered. While stellar warps are weaker than gaseous ones, they do exist. Stars are not affected directly by magnetic fields. Any mechanism based purely on magnetism would predict essentially no stellar warp at all. Yet observations show that stellar populations, especially younger stars formed in warped gas, do participate in the warp. This implies that whatever mechanism produces the warp must influence the gravitational potential itself, not just the gas. Magnetic fields cannot do this. They can push on gas, but they cannot torque stars into inclined orbits on galactic scales. Attempts were made to salvage magnetic models by treating magnetic fields as secondary agents, not creators of warps, but modifiers. In these hybrid scenarios, gravity generates the warp, while magnetic fields help maintain sharp edges or influence the detailed shape of the gas layer. This role is plausible and remains an area of active research, but it is a far cry from magnetism being the primary driver. Another observational constraint comes from the diversity of warp shapes. If magnetic fields dominated, one would expect warp properties to correlate with magnetic field strength and orientation. In practice, no such strong correlation is observed. Galaxies with similar magnetic field strengths can have very different warp amplitudes. Galaxies with weakly ordered fields can host strong warps. Conversely, some galaxies with prominent magnetic structures show minimal warping. This lack of correlation strongly suggests that magnetism is not the controlling factor. There is also a conceptual issue that cuts deeper. Magnetic fields are not external to galaxies in the way required by many warp models. They are generated by the galaxy itself through the motion of conducting gas. Treating them as an external scaffold, pulling on the disk blurs cause and effect. The disk creates the field, not the other way around. Gravity, by contrast, naturally operates at the required scale. Dark matter halos, satellite galaxies, and accreting gas exist independently of the disk and can exert coherent long-range torques. They provide a clear directionality and persistence that magnetic fields struggle to supply. By the late 20th century, consensus began to shift. Magnetic fields were recognized as important for many aspects of galactic physics: cosmic ray transport, interstellar turbulence, star formation regulation, but not as the primary origin of large-scale warps. This does not mean magnetic fields are irrelevant. They interact with warped gas. They respond to bending. In some cases, they may amplify asymmetries or influence the fine structure of the warp, but they follow the warp rather than drive it. In a warped disk, magnetic field lines are themselves warped. Polarization maps often show fields bending along with the gas layer, tracing the geometry imposed by gravitational forces. This observational fact reverses the original intuition. Instead of magnetic fields shaping the disk shapes the magnetic field. Historically, magnetic warp models played an important role, not because they were ultimately correct, but because they clarified what any successful theory must explain. They highlighted the need for coherence, longevity, and symmetry. They forced theorists to confront the winding problem, and they underscored the importance of distinguishing between forces that act directly on gas and those that shape the gravitational framework of the galaxy. In doing so, they strengthened the case for gravitational mechanisms rather than weakening it. The failure of magnetic fields as a standalone explanation also reinforced a broader lesson in galactic dynamics. Processes that dominate locally do not necessarily dominate globally. Magnetic fields are powerful on the scale of molecular clouds and spiral arms. They are subtle on the scale of entire galactic disks. Warped disks operate at the largest scales a galaxy possesses. They respond to forces that are coherent across tens or hundreds of thousands of light-years. At those scales, gravity rules. The historical fascination with magnetic warps was understandable. They offered an elegant, non-gravitational solution to a stubborn problem. But the universe proved less accommodating. The observed properties of warps, their amplitude, symmetry, persistence, and presence in both gas and stars, demand a mechanism rooted in mass, momentum, and long-term torque. Magnetic fields contribute texture, not architecture. In the end, the magnetic hypothesis did something valuable, even in its failure. It helped isolate what makes warped disks so revealing. They are not just features of gas dynamics, they are responses of entire galaxies to their invisible surroundings. And that realization points unambiguously back to gravity, slow, patient, and inescapable, as the dominant sculptor of cosmic bends and tilts. One of the earliest objections to warped galactic disks was not observational, but dynamical. Even before astronomers understood what caused warps, they believed they understood what should destroy them. A rotating disk, bent out of its plane, ought to tear its own distortion apart. The reasoning was straightforward. In a disk galaxy, different radii rotate at different angular speeds. Inner regions complete an orbit much faster than outer ones. If the disk is warped, each tilted ring should precess, slowly rotating the direction of its tilt under gravity. Because the precession rate depends on radius, the warp should wind up like a twisted ribbon. Over a few orbital periods, the coherence should be lost, smeared into a tangled, incoherent structure that quickly damps away. Yet this is not what astronomers observe. Warped disks are not rare, fleeting phenomena. They are ubiquitous. They are smooth. They are coherent across tens of thousands of light years. In many cases, they persist for billions of years. This creates a fundamental dynamical question. Why don't warps quickly disappear? Answering that question requires looking carefully at how real galactic disks behave, not as collections of independent rings, but as self-gravitating coupled systems embedded in larger gravitational fields. Differential precession is real, and it is dangerous for coherence, but it does not act in isolation. Consider a disk broken into concentric rings, each slightly tilted relative to the inner plane. If those rings were completely independent, each would precess at its own rate, and the warp would indeed wind up rapidly. This is the picture that made early theorists skeptical of long-lived warps. The flaw lies in the assumption of independence. Galactic disks are not collections of isolated rings. They are continuous, self-gravitating structures. Each ring feels not only the gravitational pull of the halo and external perturbers, but also the gravitational influence of neighbouring rings. This coupling fundamentally changes the dynamics. Disk self-gravity acts like an internal tension. When one part of the disk tilts, it pulls on adjacent parts, resisting differential motion. Instead of precessing freely, rings are partially locked together. The disk behaves less like a loose stack of plates and more like a flexible but coherent sheet. This collective behaviour allows warps to survive. The inner disk plays a particularly important role. It contains most of the disk's mass and has the strongest self-gravity. This region tends to remain flat and rigid, acting as an anchor. The outer disk, where warps are observed, is less massive and more weakly bound. It responds to external torques, but it does so while remaining gravitationally coupled to the inner disk. The result is a configuration in which the inner disk resists tilting, the outer disk yields, and the transition between them forms a smooth warp. In this coupled system, differential precession does not automatically destroy the warp. Instead, it can be balanced by self-gravity. The warp settles into a pattern where the precession rates of different radii are synchronized, or nearly so. When this happens, the warp becomes a normal mode of the disk, a stable pattern, rather than a transient disturbance. These patterns are known as bending modes. A bending mode is a collective oscillation of the disk in which large regions move coherently above or below the midplane. Unlike local ripples, bending modes involve the disk as a whole. The simplest bending mode produces an integral sine or S-shaped warp, exactly the most commonly observed configuration. In this mode, the disk does not twist chaotically, it tilts smoothly with the line of nodes, the direction along which the disk crosses the midplane, remaining well defined. The entire structure precesses slowly, if at all, as a unit. Self-gravity is essential for sustaining these modes. Without it, differential precession would dominate. With it, the disk can support long-lived bending waves that propagate slowly and maintain coherence. But self-gravity alone is not enough. If a disk were isolated, even with self-gravity, bending modes would eventually damp, energy would be redistributed, and the warp would fade. What keeps real warps alive is the presence of an external gravitational framework that continually reinforces the distortion. This is where dark matter halos, gas accretion, and satellite torques re-enter the picture. An external torque provides a preferred orientation. It does not need to be strong. It only needs to be persistent. As long as the disk is embedded in a gravitational field that is slightly misaligned with its inner plane, the bending mode can be maintained. The disk is not precessing freely. It is being gently guided. In this sense, a warp is not a static structure, nor is it a decaying one. It is a dynamically maintained configuration, continuously supported by external forces and internal coupling. The timescales involved are critical. Orbital periods in the outer disk are long, often hundreds of millions of years. Changes happen slowly. This slowness works in favour of warp longevity. External torques do not need to act rapidly. They only need to act consistently over time. Another factor that suppresses rapid winding is the distribution of mass within the disk. Real disks do not have sharp edges. Their surface density declines gradually with radius. This smooth distribution allows bending modes to extend over wide regions without encountering abrupt dynamical boundaries that would reflect or disrupt them. Gas further enhances warp persistence. Because gas is dissipative, it can absorb energy without destroying structure. When gas participates in a warp, it can radiate away excess energy while maintaining the warped geometry. This damps chaotic motions and reinforces coherent bending. In effect, gas acts as a stabilizer, smoothing out irregularities and sharpening the warp. This is one reason why gaseous warps are often cleaner and more regular than stellar warps. Gas does not resist adjustment. It settles. Stars, while collisionless, are carried along by the gravitational potential shaped by both gas and dark matter. Over time, stellar orbits adjust to the warped potential, especially for younger stars formed within the warped gas layer. This gradual adjustment allows the warp to become a genuine structural feature of the galaxy rather than a superficial gas phenomenon. There is also an important distinction between winding and precession. A warp does not necessarily need to precess rapidly to wind up. In many models, the entire warp precesses slowly as a unit, or remains nearly stationary in an inertial frame. When the precession rate is nearly constant across radius, enforced by self-gravity and external torques, winding is suppressed. This is not fine-tuning. It is an emergent property of coupled disk halo systems. Simulations demonstrate this clearly. When disks are embedded in realistic dark matter halos and allowed to respond self-consistently, warps form and persist. They do not wind up catastrophically. Instead, they evolve slowly, adjusting shape and orientation as conditions change, but maintaining coherence over billions of years. These simulations also show that warps can survive even when the driving torque varies over time. The disk does not immediately lose its warp when a satellite moves away or an accretion flow weakens. The bending mode has inertia. It retains memory of past forcing and relaxes only gradually. This memory effect further extends warp lifetimes. From a dynamical standpoint, the failure of warps to disappear quickly is no longer mysterious. It is the expected outcome of a massive, self-gravitating disk embedded in a slowly varying external potential. The early intuition that warps should wind up rapidly was based on oversimplified models. Real galaxies are more forgiving. They have the mass, coupling, and environmental support needed to sustain large-scale distortions. There is, however, a limit. Warps are not immortal. If external torques cease entirely and alignment is achieved, a warp will eventually damp. The time scale for this damping depends on disk mass, gas fraction, and halo properties, but it is long, often comparable to a significant fraction of a galaxy's lifetime. In practice, the universe rarely provides such quiet conditions for long. Galaxies continue to accrete gas, satellites continue to orbit, halos continue to evolve, the driving never fully stops. This leads to an important conceptual shift. Warps should not be thought of as deviations from equilibrium. They are equilibria, but equilibria of a galaxy interacting with its environment rather than isolated from it. In that equilibrium, the disk balances internal forces against external torques. The inner disk remains flat. The outer disk bends. The transition region supports a stable bending mode. The warp persists, not despite dynamics, but because of them. The question is no longer why warps last so long. The question becomes why any disk would ever be perfectly flat. Perfect flatness requires a rare coincidence. Alignment between disk, halo, accretion flow, and satellite population maintained over billions of years. Given the hierarchical, anisotropic nature of cosmic structure formation, that coincidence is fleeting at best. Warp longevity, then, is not an anomaly to be explained away. It is a natural consequence of how galaxies live in the universe. coupled systems shaped slowly by gravity, resisting change where they are strong, yielding where they are weak, and settling into configurations that reflect both their internal structure and their external context. The warp does not wind itself into oblivion because it is not fighting the galaxy's dynamics. It is one of their quiet expressions. When astronomers look far enough away, they are also looking far enough back in time. Light from distant galaxies began its journey when the universe was younger, denser, and far less orderly than it is today. In that early environment, disks were forming rapidly, accretion rates were high, and gravitational fields were changing on timescales comparable to a single galactic rotation. If warped disks are common in the modern universe, the expectation is not that they fade into simplicity at earlier epochs, but that they become more pronounced, more irregular, and more revealing. That expectation is borne out by observation. At high redshift, disk galaxies rarely resemble the thin, settled spirals familiar from the nearby universe. They are thicker, more turbulent, and dynamically unsettled. Their gas fractions are higher, their star formation rates are elevated, and when their disks can be resolved well enough to study their geometry, warps appear not as subtle outer bends, but as large-scale distortions that can involve much of the disk. The key difference is not merely distance, it is growth. In the early universe, galaxies were assembling mass rapidly. Gas accretion from the intergalactic medium was intense and often anisotropic. Minor mergers were frequent. Dark matter halos were evolving quickly, changing shape and orientation as they absorbed surrounding structure. In such an environment, alignment between disk, halo, and accretion flow was not the norm. It was the exception. Under these conditions, warps are not gentle peripheral features, they are integral to the disk itself. Observationally, detecting warps at high redshift is challenging. Angular resolution is limited. Surface brightness dimming makes faint outer disks difficult to see. Dust obscuration and star formation complicate interpretation. For a long time, this meant that warps were largely studied only in the nearby universe, where galaxies could be resolved in detail. That situation has changed. Deep optical and near-infrared surveys, combined with high-resolution imaging from space-based observatories and adaptive optics on the ground, have begun to reveal the structure of disks at redshifts where the universe was only a few billion years old. In these systems, disks are often visibly bent, tilted, or asymmetric. In some cases, the plane of rotation appears to change continuously with radius. In others, the disk seems broken into misaligned components. These are not isolated curiosities. Statistical studies show that high redshift disks are more frequently disturbed than their low redshift counterparts, even when obvious major mergers are excluded. The disturbances are often global rather than local, consistent with large-scale warping rather than small-scale irregularities. Kinematic measurements reinforce this picture. Velocity fields mapped through emission lines reveal disks whose rotation axes vary with radius. Instead of a single, well-defined plane of rotation, astronomers see gradual twists or abrupt tilts. These signatures are difficult to explain without invoking warped or misaligned disk structures. The amplitude of these warps is often larger than what is typically observed in nearby galaxies. Vertical displacements comparable to the disk scale height are common. In some cases, the warp involves the inner disk as well as the outskirts, indicating that the stabilizing influence of a massive, settled stellar component has not yet taken hold. This is exactly what theory predicts. In young galaxies, the stellar disk is still growing. Gas dominates the mass budget in the disk. Self-gravity is weaker, and the ability of the disk to behave as a rigid structure is limited. Under these conditions, external torques penetrate deeper. The inner disk does not act as a firm anchor. Warps can extend inward, affecting much larger fractions of the disk. Accretion in the early universe is also more chaotic. Gas flows along cosmic filaments that are thicker, denser, and more dynamic than those feeding galaxies today. The direction of accretion can change rapidly as filaments shift and intersect. Each inflow episode brings gas with its own angular momentum, often misaligned with what came before. Instead of a single, steady misalignment producing a smooth warp, the disk is subjected to a constantly changing angular momentum input. The result is not always a clean S-shaped warp. It can be a twisted disk, a series of bends, or a disk that appears tilted differently at different epochs. This chaos leaves observable signatures. High redshift disks often show large velocity dispersions. Their rotation is less dominant relative to random motion. This turbulence allows warps to form more easily, but it also makes them less regular. The disk bends, but it does not necessarily settle into a single, long-lived bending mode. Minor mergers further amplify this effect. In the early universe, the rate of minor mergers was significantly higher than it is today. Small galaxies were constantly being absorbed. Each merger delivered stars, gas, and dark matter on orbits that were rarely aligned with the host disk. Even when these mergers were not disruptive enough to destroy the disk, they injected angular momentum and torque into the system. Because the disk was still assembling, it could not easily resist these perturbations. Warps formed quickly, evolved rapidly, and were often replaced by new distortions before the previous ones could damp out. This constant reshaping leads to an important distinction between early and late warps. In the nearby universe, warps are often quasi-steady structures, maintained over long timescales by persistent but gentle torques. In the early universe, warps are often transient manifestations of rapid growth and interaction. They appear, evolve, and disappear on timescales comparable to the disk's own dynamical time. Despite this difference, the underlying physics is the same. The disk is responding to misaligned angular momentum and external gravitational influence. The difference lies in the relative strength and variability of those influences. As the universe ages, accretion slows, merger rates decline, halos settle into more stable configurations. Disks grow in mass and self-gravity. Under these conditions, warps become less chaotic and more confined to the outskirts. The inner disk flattens and stabilizes. The warp retreats outward. In this sense, warped disks trace the maturation of galaxies. A highly warped, globally distorted disk at high redshift reflects a galaxy still negotiating its identity. Its plane of rotation is not fixed. Its mass distribution is evolving. Its environment is intrusive. As time passes, the galaxy gains inertia. Its disk becomes harder to bend. Warps do not vanish, but they become gentler, more ordered, and more peripheral. This evolutionary picture is supported by simulations that follow galaxy formation across cosmic time. Early disks are thick, turbulent, and frequently misaligned. Warps are large and irregular. As the simulation progresses, disks thin, settle, and develop stable inner regions. Warps persist, but their character changes. These simulations also reveal an important asymmetry. Gas responds immediately to new accretion. Stars lag behind. As a result, high redshift disks often show strong gaseous warps, even when the stellar distribution appears smoother. This reinforces the idea that gas is the primary mediator of warp formation, especially in the early universe. Observational hints of this gas-dominated warping come from studies of high redshift galaxies using emission lines tracing ionized gas. The gas kinematics often show misalignments and twists not mirrored by the stellar light. This decoupling fades as galaxies age and stars inherit the warped potential through ongoing star formation. Another key point is that early warps are not merely scaled-up versions of modern ones. They can involve different modes. In addition to classic S-shaped warps, simulations predict and observations hint at twisted disks, where the line of nodes itself rotates with radius, producing a corkscrew-like structure. These complex warps reflect the superposition of multiple torques acting simultaneously. Such structures are rare in the nearby universe because conditions no longer favour their formation, but at high redshift they may be common. This has important implications for how early disk galaxies are classified. Some systems identified as irregular or disturbed may in fact be warped disks rather than merger remnants. Without sufficient resolution or kinematic information, the distinction can be subtle. Recognizing warps in these systems helps avoid overestimating the frequency of major mergers in the early universe. It also reframes the idea of disk stability. In the early universe, stability does not mean flatness, it means survival. A disk that remains intact while bending, twisting, and reorienting is still a disk. Warps are not signs of failure, they are signs of adaptability. Seen this way, the prevalence of warps at high redshift is not surprising. It is expected. Galaxies are forming in an environment that is still assembling itself. Their disks are flexible by necessity. As cosmic time advances, that flexibility becomes constrained. The disk's own gravity increases, external influences weaken, warps persist, but they are pushed outward and softened. What remains in the modern universe is a quieter echo of a much more turbulent past. The warped disks we observe today are survivors. They carry the imprint of early chaos, smoothed and moderated by billions of years of evolution. Their geometry reflects not only present-day forces, but a long history of growth, accretion, and interaction. In that sense, studying warps at high redshift does more than explain why early disks look distorted. It connects present structure to past process. It shows that warps are not late-time anomalies, but early intrinsic features of disk formation itself. Galactic disks were born bent. They did not begin as flat, perfect planes that later became distorted. They emerged within a universe that was already twisting them. As the universe aged, those twists became quieter, but they never disappeared. Warped disks are not relics of disturbance. They are signatures of growth. By the time warped disks were firmly established observationally, theory alone was no longer enough. The dynamics were too complex, the timescales too long, and the interactions too subtle to be captured by analytic models. Understanding how warps form, evolve, and persist required a different approach, one capable of following millions or billions of interacting particles under gravity, gas dynamics, and external influence. That approach arrived in the form of numerical simulations. From the earliest N-body experiments to modern hydrodynamical cosmological simulations, warped disks have emerged not as fragile curiosities, but as natural outcomes of realistic galaxy evolution. Simulations did not have to be forced to produce warps. Once the right ingredients were included, warps appeared on their own. The simplest numerical models treated galaxies as collections of collisionless particles representing stars and dark matter. In these early N-body simulations, disks were embedded in massive halos and allowed to evolve under gravity alone. When the halo was perfectly spherical and aligned with the disk remained flat. But as soon as the halo was tilted, triaxial, or allowed to evolve in time, the disk responded. The response was immediate and revealing. The inner disk remained largely flat, while the outer disk tilted. A smooth transition formed between the two. In projection, the resulting structure resembled the classic S-shaped warp seen in edge-on galaxies. Crucially, the warp did not quickly wind up. It persisted for many rotation periods, maintained by the steady torque from the halo. This was one of the first strong confirmations that dark matter halos could drive long-lived warps. As computing power increased, simulations grew more sophisticated. Disks were no longer rigid, idealized components. They were live, self-gravitating systems capable of responding dynamically. Halos were allowed to be triaxial, clumpy, and time-dependent. Satellites were added. Accretion was included. With each added layer of realism, warped disks became more robust rather than less. One key advance was the inclusion of hydrodynamics. Gas behaves differently from stars, and any realistic model of warps must account for that difference. Hydrodynamical simulations treat gas as a fluid subject to pressure, cooling, shocks, and dissipation. When gas is added to an N-body disk, the behavior of warps changes in important ways. Gas enhances warp visibility and coherence. In simulations, gaseous disks respond more strongly to external torques than stellar disks. They bend more sharply, extend farther, and settle into cleaner warped configurations. This matches observations remarkably well. Hydrodynamical models also naturally produce the layered structure seen in real galaxies. The interstellar disk remains relatively flat. The outer gas disk warps strongly. Young stars form within the warped gas and inherit its geometry. Older stars lag behind, producing a weaker stellar warp. This stratification was difficult to reproduce analytically, but emerges naturally in simulations. Another major success of simulations is reproducing the diversity of warp shapes. By varying halo shape, satellite population, and accretion geometry, simulations generate symmetric S-shaped warps, U-shaped warps, asymmetric warps, and twisted disks. No single configuration is required. The warp reflects the galaxy's specific history and environment. This diversity closely mirrors what astronomers observe. Simulations also reproduce the radial onset of warps. In almost every case, warps begin where the disk's self-gravity weakens and the halo's influence grows. This transition radius varies from galaxy to galaxy depending on disk mass and halo structure, just as it does in observations. Perhaps most importantly, simulations demonstrate that warps are not rare or finely tuned. In cosmological simulations, where galaxies form self-consistently from initial density fluctuations, warped disks are common. They appear even when no specific warp-driving mechanism is imposed. As long as galaxies accrete gas, interact with satellites, and live within evolving halos, warps arise. This result is difficult to overstate. It means that warps are not special features requiring special explanations. They are generic outcomes of galaxy formation. At the same time, simulations reveal important limitations. One persistent challenge is resolution. Warps occur in the outer regions of disks, where densities are low and structures are diffuse. Accurately modelling these regions requires high spatial resolution and large simulation volumes, a difficult combination. Many simulations must compromise, resolving either the inner disk in detail or the outer disk approximately, but not both simultaneously. As a result, simulated warps can sometimes be thicker or smoother than real ones. Fine structure may be lost, small-scale asymmetries may be underrepresented. This does not invalidate the models, but it does limit how precisely they can be compared to observations. Another limitation involves timescales. Simulations must run for billions of years to capture warp evolution properly. Small numerical errors can accumulate over such long integrations. Maintaining stability while allowing realistic dynamics is computationally demanding. As a result, some simulations artificially damp warps or exaggerate them depending on numerical choices. Gas physics introduces additional uncertainty. Cooling rates, star formation prescriptions, and feedback processes all influence disk structure. Strong feedback can thicken disks and suppress warps. Weak feedback can produce overly thin disks that warp too easily. Finding the right balance remains an active area of research. Magnetic fields, cosmic rays, and detailed interstellar turbulence are often simplified or omitted entirely. While these processes are not dominant warp drivers, they can influence gas dynamics and vertical structure. Their absence can subtly affect warp morphology. Another important limitation is observational comparison. Simulations produce full three-dimensional data. Observations do not. Astronomers see projections, line-of-sight velocities, and emission weighted by gas density or star formation. Translating simulation output into realistic mock observations is essential, but not trivial. Without careful comparison, it is easy to overinterpret agreement or disagreement. Despite these challenges, simulations have achieved something critical. They have reframed the warp problem from one of explanation to one of interpretation. The question is no longer whether known physics can produce warps. It can. The question is, which combination of mechanisms dominates in a given galaxy, and how that dominance evolves over time. Simulations show that no single driver is required. Dark matter halo misalignment provides a steady background torque. Gas accretion injects fresh, misaligned angular momentum. Satellite interactions add time-dependent perturbations. Self-gravity and bending modes regulate the disk's response. The warp emerges from the interaction of all these factors. This complexity is not a weakness. It is a strength. It explains why warps are ubiquitous yet diverse, stable yet evolving, simple in outline yet rich in detail. Simulations also clarify why attempts to isolate a single cause observationally have often failed. In real galaxies, multiple mechanisms act simultaneously. The warp you observe today may be maintained by halo torques, shaped by recent accretion and modified by past satellite interactions. Disentangling these contributions from a static snapshot is extremely difficult. Numerical models, by contrast, can rewind and replay galactic history. They allow astronomers to see how a warp formed, how it changed, and what sustained it. In doing so, they turn warps into chronological records rather than static features. There are still open questions. How exactly does the disk halo alignment evolve over time? What role does cold versus hot gas accretion play in shaping warp geometry? How do feedback processes alter warp persistence? How common are twisted multi-mode warps compared to simple bending modes? Future simulations, with higher resolution and more complete physics, will address these questions. They will also be guided by new observational data, especially from deep surveys that probe the outermost regions of disks with unprecedented sensitivity. What simulations have already made clear is that warped disks are not failures of disk formation, they are successes of realism. When galaxies are allowed to form and evolve under the full complexity of cosmic conditions, flat disks are the exception. Warps are the rule. In that sense, numerical simulations have done more than reproduce warped disks. They have validated a broader shift in perspective. Galaxies are not static, isolated systems seeking equilibrium. They are dynamic, adaptive structures responding continuously to their environment. The warp is one of the clearest expressions of that response, and simulations show that it arises naturally when galaxies are allowed to be what the universe actually makes them. A warped galactic disk is not just a distortion to be explained, it is a measurement being made by the galaxy itself. Every bend in a disk encodes information about forces that cannot be seen directly. The stars trace only a fraction of a galaxy's mass. Gas reveals structure farther out, but still responds to gravity dominated by something invisible. The warp is the visible reaction of a luminous disk to that hidden framework. In this sense, warped disks function as probes, not of the disk, but of the environment surrounding it. This idea represents a shift in how warps are used scientifically. Early work treated them as problems. Modern work treats them as diagnostics. The fundamental reason warps are useful probes is simple. The outer regions of galactic disks are weakly bound and dynamically slow. Orbital periods are long. Self-gravity is reduced. External forces that would be negligible in the inner disk become dominant. As a result, the geometry of the warp is exquisitely sensitive to whatever is shaping the gravitational potential beyond the visible galaxy. Dark matter halos dominate that potential. A disk embedded in a spherical halo would feel no preferred direction. A disk embedded in a flattened, tilted or triaxial halo will. The disk responds by bending. The details of that bend, where it begins, how steep it is, whether it is symmetric or lopsided, whether it twists with radius, depend directly on the halo's shape and orientation. This makes warps one of the few observational tools capable of constraining halo geometry without relying on indirect statistical methods. Rotation curves tell us how much dark matter there is. Warps tell us how it is arranged. The most basic inference comes from warp onset radius. In many galaxies, the warp begins at the radius where the disk's contribution to the gravitational potential drops below that of the halo. This transition point provides a handle on how concentrated the halo is and how strongly it couples to the disk. A massive, compact disk resists warping farther out. A lighter disk yields earlier. The amplitude of the warp adds another layer of information. Strong warps imply either a strongly misaligned halo, a significantly non-spherical halo, or persistent external torques acting in concert with the halo. Weak warps suggest closer alignment or a more spherical mass distribution. Importantly, these conclusions do not require knowing the absolute mass of the halo, only its geometry. Warp symmetry is even more revealing. A clean, symmetric S-shaped warp suggests a relatively coherent torque acting across the disk. This is consistent with a stable halo whose symmetry axis is tilted relative to the disk plane. An asymmetric warp, where one side bends more strongly than the other, points toward a halo that is triaxial, lopsided, or perturbed by recent accretion or satellite interaction. Twisted warps, where the line of nodes rotates with radius, indicate time-dependent torques. The halo's orientation may be changing. Accretion may be arriving from different directions at different times. The disk is responding not to a fixed structure, but to an evolving one. These inferences are not speculative, they are supported by detailed modelling. When astronomers fit warp geometries using dynamical models, they find that only certain halo configurations reproduce the observed shapes. Spherical halos fail. Perfectly aligned halos fail. Warps demand asymmetry. They demand misalignment. They demand structure in the dark matter distribution. This is particularly powerful because it breaks a long-standing degeneracy in galactic dynamics. Rotation curves alone cannot distinguish between different halo shapes that produce the same radial force profile. Warps respond to vertical and azimuthal forces. They break that degeneracy. The Milky Way provides a clear example. The warp of the Milky Way's gas disk is asymmetric and twisted. Its line of nodes is not fixed. Its amplitude differs between the northern and southern sides. Modelling this geometry points toward a dark matter halo that is not spherical and not perfectly aligned with the inner disk. It also suggests that the halo may be responding to ongoing accretion and satellite interactions. Independent lines of evidence, stellar streams, satellite motions, and halo substructure point in the same direction. The warp is consistent with a halo that is dynamically active rather than static. This convergence is not accidental. Warps are sensitive to the same underlying physics that shape satellite orbits and stream precession. They provide an integrated response of the disk to the total gravitational field. Beyond halo shape, warps are sensitive to external torques from the cosmic environment. Galaxies do not sit in isolation. They occupy nodes in the cosmic web, connected by filaments of dark matter and gas. These filaments exert gravitational influence, even when they are diffuse. Gas flows along them. Satellites arrive along them. Angular momentum is delivered preferentially along their axes. A disk embedded in such an environment experiences a net torque that reflects the orientation of the surrounding large-scale structure. Over time, that torque imprints itself on the disk as a warp. This means that warp orientation can correlate with cosmic environment. Statistical studies show that warps are not randomly oriented. In some samples, warp axes align preferentially with nearby filaments or large-scale density gradients. This alignment is weak but significant. It suggests that warps retain memory of how galaxies are fed by the cosmic web. In this sense, a warp is not only a probe of a galaxy's halo, but of its place in the universe. The sensitivity of warps to environment also explains why similar galaxies can have very different warp properties. Two disks with comparable mass and rotation curves can look very different if one is fed by a steady filament and the other by intermittent, misaligned accretion. The difference does not lie in the disk itself, but in the direction and variability of external torques. Satellite populations further modulate this response. A galaxy surrounded by many satellites on inclined orbits will experience time-dependent torques that produce asymmetric or evolving warps. A galaxy with few satellites may show a cleaner, more symmetric structure dominated by halo misalignment and gas accretion. The warp reflects the combined gravitational influence of all companions, luminous or dark. Because satellites themselves are embedded in the halo, their influence is amplified. They perturb the halo, which then perturbs the disk. This indirect coupling makes warps sensitive to substructure that is otherwise extremely difficult to detect. In effect, the disk acts as a detector. This sensitivity comes with a price. Warps are influenced by multiple factors simultaneously. Interpreting a single warp in isolation is challenging, but this complexity becomes an advantage when many warps are studied statistically. Across large samples, patterns emerge. Correlations between warp amplitude and environment. Trends with galaxy mass and gas fraction. Differences between field galaxies and group members. Each correlation constrains a different aspect of halo structure and cosmic context. Modern surveys are beginning to exploit this systematically. Deep radio observations map neutral hydrogen far beyond the optical disk, revealing warp geometry with high precision. Optical and infrared surveys trace stellar warps and their dependence on age. Kinematic data add velocity information, allowing three-dimensional reconstruction of warped disks. Combined with simulations, these observations allow astronomers to invert the problem. Instead of asking what causes a given warp, they ask what halo and environment are required to produce it. This inversion is powerful because it bypasses many uncertainties in direct dark matter detection. Dark matter does not emit light, but it bends galaxies. Warps are among the cleanest expressions of that bending. There is also a temporal aspect to this probing. Warps evolve slowly. They integrate the effects of torques over long timescales. This makes them insensitive to short-lived disturbances and sensitive to persistent ones. A brief interaction may leave tidal debris that fades quickly. A long-term misalignment leaves a warp that persists. As a result, warps are better probes of sustained structure than of transient events. They tell us not just what happened recently, but what has been happening for billions of years. This makes them complementary to other tracers. Stellar streams reveal localized interactions. Satellite motions reveal present-day halo structure. Warps reveal long-term gravitational context. In galaxies at higher redshift, this probing becomes even more valuable. Direct measurements of halo shape are extremely difficult at early times, but warped disks, when detected, provide clues to how halos were assembled and how chaotic their environments were. Stronger, more global warps at high redshift imply halos that were rapidly evolving and misaligned with forming disks. Gentler warps at low redshift reflect halos that have settled. In this way, the evolution of warp properties traces the evolution of dark matter structure itself. This perspective also reframes the idea of disk equilibrium. A warped disk is not out of equilibrium in a dysfunctional sense. It is in equilibrium with an asymmetric, evolving gravitational field. The warp is the equilibrium shape of the disk given its environment. Seen this way, flat disks are special cases, systems whose halos, accretion flows, and satellite populations happen to align. Warped disks are the general case. Using warps as probes therefore requires abandoning the assumption that flatness is the default. Instead, the default is response. The disk responds to halo shape. It responds to accretion direction. It responds to satellite torques. The response is visible, measurable, and persistent. The challenge going forward is not to decide whether warps are useful probes, but to refine how they are used. This requires better data, better models, and careful separation of overlapping effects. It requires combining warp geometry with kinematics, environment, and stellar populations. But the payoff is significant. Dark matter halos are among the most elusive structures in the universe. Warped disks offer a rare opportunity to study their shape, orientation, and evolution using visible matter alone. They turn galaxies into instruments, slow, massive, gravitational instruments that integrate the invisible forces acting upon them. Every warp is a measurement that has already been taken. The task is to learn how to read it. In that reading, the warp ceases to be a curiosity or a complication. It becomes what it always was, a signal. Not all warp disks are gentle bends at the outskirts of otherwise orderly galaxies. Some systems push the concept of a warp to its limits, revealing geometries so extreme that they force astronomers to refine definitions, separate related phenomena, and confront the boundaries between disks, interactions, and outright structural reconfiguration. These extreme and unusual cases are not statistical noise, they are critical tests. They show what happens when the same physical mechanisms that produce ordinary warps operate under more dramatic conditions, or when multiple mechanisms overlap. They also clarify what a warp is and what it is not. Among the most striking examples are polar disk galaxies. A polar disk galaxy hosts two large-scale disk components that rotate in nearly perpendicular planes. One disk resembles a conventional galactic disk, typically dominated by stars and aligned with the galaxy's main stellar body. The other disk, often rich in gas and young stars, orbits along a plane close to 90 degrees relative to the first. At first glance, polar disks look like extreme warps taken to an absurd conclusion, but dynamically they represent a distinct regime. In a classical warp, the disk remains continuous. The inner and outer regions are connected by a smooth transition in orientation. Angular momentum changes gradually with radius. In polar disk systems, by contrast, the angular momentum changes abruptly. Two dynamically coherent disks coexist, each with its own stable plane. This configuration is only possible if the gravitational potential allows it. In practice, this means a dark matter halo that is close to spherical or has a symmetry axis aligned in a way that can support perpendicular orbits without rapid precession. If the halo were strongly flattened or misaligned, one of the disks would quickly destabilize. Polar disks therefore provide unusually strong constraints on halo shape. Their very existence implies halos that are rounder than average or dynamically accommodating. This makes them valuable laboratories for studying dark matter geometry in a way ordinary warps cannot. Formation scenarios for polar disks differ from those of standard warps, but they are connected by the same underlying physics, misaligned angular momentum. In many cases, polar disks are thought to form through the accretion of gas from a direction nearly perpendicular to the original disk, often delivered by a minor merger or filamentary inflow. If the gas arrives coherently and in sufficient quantity, it can settle into a stable polar orbit, rather than being gradually twisted into the original disk plane. This is a case where misalignment does not produce a warp, but a second disk. Severely twisted systems occupy an intermediate category between ordinary warps and polar disks. In these galaxies, the disk orientation changes continuously with radius, but by such a large amount that the outer disk may approach orthogonality with the inner disk. The line of nodes itself rotates with radius, producing a corkscrew-like geometry. These twisted warps are rare in the nearby universe, but more common at higher redshift, where accretion is chaotic and disk self-gravity is weaker. They represent situations where no single torque dominates. Instead, the disk responds to a sequence of changing forces, halo reorientation, shifting accretion flows, and satellite interactions, without ever settling into a simple bending mode. From a dynamical standpoint, twisted warps are still warps. The disk remains continuous. Orbits are still roughly circular. There is no sharp kinematic break. But the geometry is more complex than the textbook S-shape, and interpreting it requires careful modelling. These extreme cases highlight the importance of distinguishing warps from other disk phenomena that can look similar in projection. One common source of confusion is disk flaring. A flared disk increases in thickness with radius. The vertical scale height grows, but the midplane remains flat. In edge-on projection, a flare can resemble a warp, because the outer disk appears puffed up above and below the plane. The key difference is symmetry. In a flare, the thickening is symmetric above and below the midplane. There is no systematic shift of the midplane itself. In a warp, the midplane moves. Gas and stars on one side of the disk are preferentially displaced upward, while the opposite side moves downward. Kinematic data are decisive here. In a flared disk, rotation remains symmetric about the central plane. In a warped disk, the rotation plane itself tilts with radius. Without velocity information, the two can be difficult to distinguish, especially in distant galaxies. Another related phenomenon is a global disk tilt. A tilted disk is a disk whose entire plane is inclined relative to some reference frame, for example, relative to a surrounding stellar halo or bulge. This is not a warp. There is no change of orientation with radius. The disk behaves as a rigid body. Tilts can arise through mergers or reorientation of the angular momentum axis, but they lack the radial structure that defines a warp. Observationally, tilts are identified by a constant orientation across the disk, whereas warps show a gradient. This distinction matters because tilts and warps have different implications. A tilt suggests a global realignment event. A warp suggests ongoing torque and differential response. Tidal distortions add another layer of complexity. Close interactions between galaxies can stretch disks, pull out tidal tails, and generate asymmetries that resemble warps in projection. In such cases, the distortion is not a stable bending mode, but a transient response to a strong gravitational encounter. The signatures of tidal distortion include strong non-circular motions, asymmetry between approaching and receding sides of the disk, and often the presence of visible companions or tidal debris. Warps, by contrast, preserve ordered rotation and lack obvious signs of recent violence. This distinction is not always clear-cut. Minor mergers and satellite interactions can both warp a disk and produce faint tidal features. The difference lies in scale and coherence. Warps are large-scale, smooth, and long-lived. Tidal distortions are often sharper, more localized, and evolve more rapidly. Another extreme case that challenges classification is the presence of counter-rotating or misaligned gas disks. Some galaxies host gas that rotates in the opposite direction to the stars, or in a plane significantly inclined relative to them. These systems often result from the accretion of external gas with angular momentum opposite to that of the existing disk. If the accreted gas is small in mass, it may form a warped outer layer that gradually aligns or dissipates. If it is substantial, it can form a distinct disk component. The transition between these outcomes is gradual, not sharp. This again emphasizes that warps, polar disks, and misaligned disks are not separate phenomena, but points along a continuum defined by angular momentum, misalignment, mass ratio, and timescale. Extreme warps also test the limits of disk stability. In very low mass disks or gas-dominated systems, self-gravity may be too weak to maintain coherence. In such cases, warps can fragment into corrugations, lopsided distortions, or irregular vertical structure. These systems blur the line between warped disks and irregular galaxies. Conversely, in massive disks with strong self-gravity, even large external torques may produce only mild warps. The disk resists bending, confining the distortion to the outermost regions. This dependence on disk mass helps explain why extreme warps are more common in certain galaxy populations, gas-rich, low-mass disks, and galaxies undergoing rapid accretion. From an observational standpoint, classifying extreme cases requires combining morphology with kinematics. Images alone are insufficient. Velocity fields reveal whether the disk remains rotationally supported and coherent, or whether it has been dynamically disrupted. This is particularly important at high redshift, where resolution limits can make warped disks look chaotic or fragmented. Without kinematic confirmation, warps can be misidentified as merger remnants, leading to overestimates of merger rates. Recognizing warped disks in extreme forms therefore has broader implications for galaxy evolution. It affects how disks are counted, how interactions are inferred, and how the timeline of disk settling is reconstructed. At a deeper level, extreme cases reinforce a central lesson of warp studies. Flatness is not fundamental. It is contingent. Disks can bend, twist, split, and reorient without ceasing to be disks. Angular momentum is not fixed. It is negotiated continuously with the environment. Warps are the visible trace of that negotiation, and extreme warps are cases where the terms are unusually dramatic. Polar disks show that perpendicular configurations can be stable under the right conditions. Twisted disks show that alignment can vary continuously with radius. Misaligned gas disks show that accretion can overwhelm inherited structure. Each case extends the basic warp concept into new territory. Distinguishing warps from flares, tilts, and tidal distortions is therefore not just a taxonomic exercise, it is a way of understanding which physical processes are dominant in a given system and on what timescale they act. A flare speaks of internal vertical heating. A tilt speaks of global reorientation. A tidal distortion speaks of recent violence. A warp speaks of long-term, gentle torque. Extreme warps speak of complexity. They remind us that galaxies are not idealized disks responding to a single force. They are layered, adaptive systems responding to multiple influences at once. The more extreme the case, the more clearly that complexity is revealed. In this light, the most unusual warped disks are not outliers to be explained away. They are boundary conditions that define the full range of galactic behavior. They show how far a disk can be pushed without breaking, and where it finally does. And in doing so, they sharpen our understanding of what a warp truly is. Not a defect, not a disturbance, but a structural response shaped by gravity, history, and environment, expressed in geometry. For decades, warped galactic disks have been studied in fragments. A nearby galaxy mapped deeply in neutral hydrogen. Another observed edge-on in optical light, a handful modelled in detail. Each piece added insight, but none provided a complete picture. That limitation has never been conceptual. It has always been observational. Warps live where galaxies fade. They emerge in the faint outskirts, where gas densities are low, starlight is weak, and surface brightness drops below the reach of traditional surveys. They evolve slowly, requiring long temporal baselines to understand, and they respond to forces, dark matter geometry, gas inflow, satellite torques, that are themselves difficult to observe directly. The next phase of warp research is therefore not about new ideas, it is about new data. Over the coming years, a new generation of surveys and instruments will dramatically expand what can be measured, mapped, and compared. For the first time, warped disks will be studied statistically across environments, masses, and cosmic time. Not as curiosities, but as standard components of galaxy structure. The most transformative advances will come from radio astronomy. Neutral hydrogen remains the single most powerful tracer of warped disks. It extends farther than stars, responds sensitively to external torques, and preserves ordered kinematics even in the faint outskirts. Historically, hydrogen surveys have been limited by sensitivity and resolution. That is changing. Next-generation radio arrays are designed to detect extremely low column densities of neutral hydrogen, reaching well beyond the traditional edge of galactic disks. This will allow astronomers to map warps not just where they are obvious, but where they begin, capturing the transition region between flat inner disk and bent outer layers with unprecedented clarity. Equally important, these surveys will observe thousands of galaxies rather than dozens. This statistical leap matters. With large samples, patterns emerge, correlations between warp amplitude and galaxy mass, between warp orientation and environment, between warp symmetry and satellite population. These correlations cannot be established from isolated case studies. High-resolution velocity fields will also be crucial. Warps are three-dimensional structures. Imaging alone reveals only projection. Kinematics reveal geometry. By mapping line-of-sight velocities across warped disks, astronomers can reconstruct the full orientation of the disk as a function of radius. This allows direct measurement of bending modes, line-of-nodes twists, and precession signatures. It also allows flares, tilts, and tidal distortions to be distinguished cleanly from true warps. These data will finally allow models to be tested decisively. Dark matter, halo misalignment, predicts specific warp geometries and radial trends. Gas accretion predicts others. Satellite torques produce characteristic asymmetries and time variability. Until now, many of these predictions have overlapped observationally. With deeper, cleaner data, that overlap will shrink. Radio surveys will also extend warp studies into new environments. Group galaxies, cluster galaxies, and truly isolated field galaxies can be compared systematically. This matters because different environments emphasize different mechanisms. Satellite interactions dominate in groups. RAM, pressure, and halo stripping dominate in clusters. Smooth accretion dominates in the field. If warps persist across all environments but change character, that variation itself becomes diagnostic. Optical and infrared surveys will play an equally important complementary role. While gas reveals warp geometry most clearly, stars reveal warp history. Stellar populations carry age information. If a warp has persisted for billions of years, stars of different ages should reflect that persistence differently. Young stars should trace the gas warp closely. Old stars should show a muted or lagging response. Deep optical mapping of stellar outskirts will make this test possible. Modern surveys are pushing surface brightness limits far below what was once thought achievable. Faint stellar halos, thick disks, and outer disk populations are now being mapped routinely. As this depth improves, stellar warps will be traced farther out and with greater confidence. This will allow astronomers to answer a long-standing question: how deeply do warps penetrate the stellar disk? If stellar warps are confined to young populations, accretion-driven models gain support. If older stars participate more strongly than expected, long-term halo torques become harder to avoid. The relative strength of stellar and gaseous warps will become a quantitative constraint rather than a qualitative impression. Another frontier lies in time. While galaxies evolve too slowly for direct time-lapse observation, surveys at different redshifts provide snapshots at different cosmic epochs. With sufficiently large samples, warp statistics can be traced across time. Are warps stronger at earlier epochs, more chaotic, more global? Do they retreat outward as disks mature? Does the fraction of warped galaxies change with redshift? Preliminary answers exist, but future surveys will make them precise. This temporal dimension is critical because it separates cause from consequence. Halo misalignment, accretion geometry, and satellite populations all evolve over cosmic time. Warps respond to that evolution. By mapping how warp properties change with redshift, astronomers can infer how the dominant drivers themselves change. There is also a synergy with stellar stream studies. Stellar streams trace the orbits of disrupted satellites. They map the gravitational field of the halo directly. Warps trace the disk's response to that same field. When both are observed in the same galaxy, the constraints multiply. A halo shape inferred from streams can be tested against the warp geometry. Agreement strengthens the model. Disagreement reveals missing physics. This multi-probe approach will be one of the most powerful outcomes of upcoming surveys. Numerical simulations will evolve alongside observations. As data improve, simulations will be forced to become more realistic. Halo shapes, accretion histories, and satellite populations will be tuned not to reproduce individual warps, but entire populations of them. This population-level matching is far more demanding. and far more informative. It will allow astronomers to ask not just whether a mechanism can produce a warp, but whether it produces the right distribution of warps. Does a given cosmological model predict the observed fraction of symmetric versus asymmetric warps, the correct dependence on galaxy mass, the observed relationship with environment? These questions are finally becoming answerable. There is also an emerging opportunity to use warps as cosmological tools. Because warp geometry responds to large-scale structure, statistical alignment of warps with filaments and density gradients provides information about how angular momentum is acquired. This links galactic structure directly to cosmological initial conditions. In this sense, warps connect the smallest scales of galaxy disks to the largest scales of the universe. All of this points toward a shift in emphasis. For much of their history, warped disks were studied as secondary features, complications to be corrected for, anomalies to be explained away. The coming generation of observations will reverse that perspective. Warps will become primary data. They will be measured systematically, modelled quantitatively, and used diagnostically. They will inform halo geometry, accretion history, satellite dynamics, and environmental influence. They will no longer be background features. They will be foreground signals. There is one more, subtler implication. As warp origins become constrained, the relative importance of different physical processes will become clearer. It may turn out that no single mechanism dominates universally. Instead, different galaxies may inhabit different warp regimes depending on mass, environment, and evolutionary stage. That outcome would not be a failure of theory. It would be a confirmation of complexity. Galaxies are not uniform systems evolving along a single track. They are adaptive structures responding to context. Warps are one of the clearest expressions of that adaptability. Future observations will not reduce warps to a single cause. They will map the space of causes, and in doing so, they will complete a transition that began quietly decades ago when astronomers first noticed that disks were bending where they were supposed to be flat. What was once an inconvenience will become a tool. What was once a mystery will become a measurement. And warped galactic disks will finally be understood not just as things that happen to galaxies, but as things galaxies use to reveal the invisible structures that shape them. A warped galactic disk is easy to dismiss as a geometric curiosity, a bend at the outskirts, a deviation from an idealized plane, something to be modelled, corrected for, or averaged away. But taken seriously, warps tell a much larger story. Not just about disks, but about what galaxies are, how they live, and how deeply they are embedded in the structure of the universe. At its core, a warp is evidence that a galaxy is not a closed system. If galaxies were isolated, if they formed, settled, and evolved without further interaction, their disks would relax into stable, flat configurations. Any bending would damp away, any misalignment would be temporary. The persistence and ubiquity of warps tell us that this picture is incomplete. Galaxies remain open to their surroundings for their entire lives. They continue to accrete gas. They continue to interact gravitationally with companions. They remain embedded in dark matter halos that evolve over time. They sit within filaments of the cosmic web that channel matter, momentum, and torque. A warped disk is the visible response to this openness. In this sense, a warp is not a flaw in galactic structure. It is a signature of connection. The inner regions of a galaxy often give the illusion of isolation. Stars orbit in orderly patterns. Spiral arms wind predictably. Bars rotate steadily. These regions are dominated by the galaxy's own gravity. They are internally regulated, but the outskirts tell a different story. There, the galaxy's grip weakens. External influences take over. The disk becomes flexible. The warp marks the boundary between self-dominated structure and environmental influence. This boundary is not sharp. It is gradual, and that gradualness is important. It means that galaxies are not divided into an inside that is autonomous and an outside that is chaotic. Instead, they are continuously negotiating with their surroundings. The warp is the geometry of that negotiation. This has profound implications for how galaxies are understood conceptually. For much of the 20th century, galaxies were treated as equilibrium systems. Their structure was assumed to reflect internal balances, gravity versus rotation, pressure versus collapse. External effects were treated as disturbances, deviations from the norm. Warped disks invert that logic. They show that equilibrium itself includes external influence. A galaxy can be dynamically stable while still being bent. Stability does not require isolation, it requires balance. In a warped disk, that balance is between internal self-gravity and external torque. The inner disk holds its shape, the outer disk yields. The resulting structure is neither chaotic nor rigid, it is adaptive. This adaptiveness reveals something essential about galaxy evolution. It is ongoing. Galaxies do not complete their formation and then merely age. They continue to grow, slowly but persistently. Gas accretion does not stop when the disk forms. Satellite interactions do not end when the last major merger is over. Dark matter halos do not freeze into final configurations. Warped disks are living structures because galaxies are living systems. They change shape, not because something has gone wrong, but because something is still happening. This perspective reframes the relationship between galaxies and the cosmic web. The cosmic web is not just a backdrop. It is an active participant in galaxy evolution. Filaments guide gas inflow, they deliver satellites, they impose preferred directions for angular momentum. Over time, these directions change as structure grows and rearranges. A disk galaxy embedded in this web cannot ignore it. The angular momentum of accreted material reflects filament orientation. The gravitational pull of the surrounding mass distribution reflects web geometry. The disk responds. The warp is that response made visible. This connection explains why warp orientations are not random. They often correlate weakly but significantly with large-scale structure. They remember where material came from. They encode how the galaxy is fed. In this way, a warp links scales that are otherwise difficult to connect. It ties kiloparsec scale disk structure to megaparsec scale cosmic architecture. It turns a galactic feature into a cosmological tracer. This is rare. Most galactic structures are dominated by internal physics. Spiral arms reflect disk instabilities. Bars reflect angular momentum redistribution. Bulges reflect early collapse and mergers. Warps are different. They are shaped primarily by what lies beyond the visible galaxy. They are among the clearest examples of external causation in galactic morphology. This also explains why warps are so diverse. Galaxies do not share identical environments. Some sit in dense groups, some lie along prominent filaments. Some are fed steadily from one direction, others accrete episodically from many. Each history leaves a different imprint on the disk. Uniformity would be more surprising than diversity, yet despite this diversity, warps share common features. They begin where disks become weak. They grow gradually. They preserve ordered rotation. They persist. These commonalities reflect universal physics, gravity, angular momentum, and slow time scales. The details vary. The principle does not. Warped disks also challenge a deeply ingrained assumption in astronomy that flatness is fundamental. Flat disks are often treated as the default, with warps described as deviations. But from a formation standpoint, flatness requires alignment. Alignment requires coincidence. In a universe where angular momentum is acquired stochastically and structure is anisotropic, perfect alignment is unlikely to persist. Warped disks may therefore be more natural than flat ones. Flat disks may represent temporary alignments, moments when disk, halo, accretion flow, and environment happen to line up. Warps appear when that alignment drifts, which it almost inevitably does. Seen this way, warps are not signs of disturbance. They are signs of realism. They tell us that galaxies do not exist in idealized potentials. They exist in the actual universe, with all its asymmetry and motion. There is also a philosophical implication that runs deeper. Warped disks blur the boundary between object and environment. Where does the galaxy end? At the edge of the stellar disk? The gas disk? The dark matter halo? The region where the warp begins? A warp suggests that the galaxy's structure cannot be fully defined without reference to what surrounds it. The galaxy is not an isolated object, but a node in a network. Its shape is partly determined elsewhere. This challenges the language often used to describe galaxies. Words like isolated, undisturbed, and relaxed take on new meaning. A galaxy can be undisturbed in appearance and still be deeply influenced. It can be relaxed internally while responding externally. Warped disks embody that duality. They are calm and orderly, and they are responsive. This duality also explains why warps are so valuable scientifically. They are sensitive without being fragile. They record external influence without being erased by it. They integrate weak forces over long timescales, turning persistence into signal. Few galactic features do this as cleanly. Looking forward, the broader meaning of warped disks will only deepen as observations improve. As more galaxies are mapped in detail, warps will no longer be exceptions to be explained, but expected features to be measured. Their statistics will become constraints, their geometry will become data. They will inform models of halo evolution, accretion geometry, and cosmic web dynamics. They will help connect galaxy evolution to large-scale structure in a direct, observable way. In that future, warped disks will not be described primarily in terms of what bends them, but in terms of what they reveal. They reveal that galaxies grow continuously, that they remain connected, that their structure is shaped as much by what lies beyond them as by what lies within. They reveal that the universe does not neatly separate scales. The shape of a disk remembers the shape of the web. And perhaps most importantly, they reveal that order in the universe is not static, it is negotiated. A warped disk is order under influence, structure under pressure, stability without isolation. It is the geometry of belonging. Galaxies are not islands, they are participants, and the warp is the quiet evidence written into their shape.